Hey, Joe in Italia. Ah, shoot. Go ahead, unmute again. So you've
Yeah.
got so you've got your
Is it?
Italian
Yeah. Buonasera. Hi, everybody.
so you've got your Italian call sign.
No, I didn't.
You don't have your
It's a very,
Italian call yet.
yeah, it's a very long story. I don't want to go into that,
Okay.
to be honest. I'm looking for an American one, but I didn't work out my way yet.
Mhm. So, um, have you gotten in touch with anybody who is administering exams by chance?
No, no,
Okay, because that's
not sure. Not sure if I can. To be honest, I dropped you an email this morning. I don't know if you saw it, but my issue is that I don't have what to say, mail address in the US, so that's no problem. I saw your email, or I think it was from you, about the mandatory having an English written passport, which of course I have. But other than that, I have nothing else, so I'm not sure. I'm not for sure that the local amateur radio here in Italy do one session, exam session for American call sign, but I have no idea how do they work. So,
yeah.
to be honest, I know that they charge for that. So, I'm not exactly, I think this is against our ethic, so I prefer to do my way and see how it goes.
Hey,
All right, as our class is building up today, take this opportunity to ask questions before we get started. This is a good chance you get dedicated time.
Scott, I have a question. This is
Oh,
John from
good,
San Diego.
good.
So I got into this actually back in the summer. I told you yesterday I was quite overwhelmed with the amount of material. So I'm really happy for taking your class, and you do it so well and present it so efficiently. And the other thing too is I had actually purchased this product, this ham radio by ARRL.
Which is a good reference book.
It's a great reference book, but it's not meant for people who've never had this stuff. So that other supplemental guide that you provided is really, really good.
Well,
Um,
the supplemental guide that the guide that I use
hmm
is an overview-ish book,
hmm
right? The ARRL book, if you're willing to take 6 months to practice
Yeah, there you
and
go.
read the
That's
whole thing,
right.
it's really good.
Yeah, no, I agree. I agree. Anyway, so I wanted to get into this because I have kids throughout the United States. I have four kids,
Hmm.
and my whole thing is to be able to get in contact with them, given that like the circumstances on the East Coast with those two hurricanes.
Hmm.
And however, that would I realized that would entail them getting a ham radio license as well.
Yep.
So my question is this: if can I communicate to what is a general radio mobile GRMS? Is that the term?
GMRS,
Yeah,
General Mobile
general.
Radio Service.
Yeah. Can I communicate to them via that? Are there bands that we share at all?
No.
Okay.
And those are all local. I
Right.
mean,
Okay.
they're all
Okay.
line of sight. There's no long distance GMRS.
Okay, so they don't have access to their own kind of repeater system or anything like that.
They do, but they don't go long distances. However,
Okay.
um, th there are other ways to there are other things you can do. For
Hmm.
instance, there's something called WinLink, and
Okay.
and WinLink is a radio-based email system that basically gets you the ability to send emails to other hams in different places over digital communications. Um, if the internet is up and you want to send an email to a non-ham, I believe there are bridges
Okay.
that will allow that to work.
Okay.
Now, part of that also is that, the content of the email is going to be different than, what you would typically get to send just by email because first of all, it's not private.
Right.
There's no
Okay.
expectation of anything being private
Okay.
because you can't encrypt anything. And, it follows the same rules as, radio, it's talking on the air, which is no profanity and stuff like that, whether
Right.
it's written or otherwise. So,
Okay.
but yeah, there are a lot of hybrid technologies. One of the other things that we do, one of the other things we do is there's a lot of hybridization of all this technology
Okay.
with regard to internet and um, with regard to the internet and radio bridges and things like that. And now
Mhm.
we have something that, let's see if this can, come on. I don't have it on the, I have it on the phone, but it's not looking very good. So
Okay.
it's
Yeah.
called, it's called Echolink.
Oh, I've read about Uplink too. Okay.
Yeah.
And somebody mentioned the sat phone, and my one son has access to Starlink. Oh, I
Mhm.
see. I see. Okay,
So this
got
is
it.
Echolink. Echolink basically is if you have a license, you can sign up for an Echolink account. Any repeater or other person who is signed up as a node
Hmm.
or as a bridge, um, or as just a repeater that is tied into the system,
Right.
where possible, it will it will utilize the internet link and like I can when I'm traveling, for instance,
Hmm.
uh, I've been in Austria working, South
Hmm.
America working. If I had an internet connection, I would sign in as myself, using my
Hmm.
call sign and be able to access my local repeater here in Eugene and talk to people.
Oh, okay. That's it. Okay, that's a way to. Okay, but
Yeah,
you have to have access to the internet.
you have
Internet
to have
connection
internet
down.
access.
Mhm. Right. Okay. All right. Those are
Now,
great ideas.
now
And
also notice the sat phone that was brought up. You've
yeah.
got
Mhm.
you've got Starlink, et cetera, et cetera.
Right. Right.
Those are internet connections. So you can go and consider that also to be,
Right.
use it directly or use it as a hybridization,
Okay.
you know.
And not to take up anybody's time, but for somebody new like me, who just wants to get in easy, is there, other than Amazon, is there a web source that you would suggest to go to look at initial radio options?
Oh yeah. Yeah. Amazon's actually quite a poor one.
Oh, poor,
Yeah.
bad, right?
Yeah.
Yeah, it's all, yeah. That's what I was thinking.
Uh-huh. Here.
Hey, good
Ham
morning, Scott. I have a two-part quick question.
ham radio outlet. I'll just bring
Okay.
that up. There's a whole bunch of very, very reputable dealers who sell actual gear.
Oh, it really
Perfect.
is.
Gigaparts. There's MTE in Texas. There's, 4 or 5 of them in the United States that sell ham gear.
Okay, perfect. Thank you.
All right, you're up.
Is that me?
Yep.
Sorry about that. Okay. So for the exam tomorrow, if it's already full, how do we go about scheduling for a
You
future exam? I may have
okay.
missed that part.
So as of right now, I'm going to say it again because you're all still kind of early birds, which is good. Um, and I don't want to, I don't want to start a battle, but there's still one seat. We had a couple people leave yesterday, their seats, either because they scheduled for another date or they took an exam already. So there is one open seat.
Okay. And my second part of that question is, in the event that the test isn't passed the first time, do you have to retake the class or can you
The
just
class has
retake the
nothing to do
exam?
with the exam.
Okay.
Absolutely nothing. The class has absolutely nothing to do with the test.
Okay. Gotcha. Thanks.
Hmm. I'm here for supplemental backup information and a little bit of help.
Which you
And
do
to
very well.
thank you. And to teach you guys the background. So Jude, you might have the distinction of being the youngest one here.
That's funny.
And where are you located?
I'm in Eugene. We just moved here, so
Cool.
yeah. Gonna be taking the test tomorrow, so
Excellent.
yeah, I'm
And where
excited.
and what school and stuff?
I'm going to South Eugene right now.
Oh, cool.
Yeah.
So you were actually in Danny's class, right?
No, I don't
You
think
weren't.
so. This is the first class I'm taking.
No, no. Danny is in Tubman.
I don't know who that is.
Oh, but are you in one of Asher's classes or this is
Mm.
my kid goes to South
Oh,
and
cool.
there's a ham club at South.
Oh, okay. I didn't
You
know about that.
you didn't do you know Asher Tubman?
No,
Physics teacher. What grade are you in?
I'm in ninth grade.
Oh, that's cool. Okay.
Yeah.
Yeah. We're building a station in
Okay.
the IHS wing.
Okay, wow. That's cool.
We have a $17,000 grant to spend and we have
That's
a dedicated room to build out and all that other good stuff. So, wow,
that's
how
really cool.
lucky.
Yeah, I gotta join that club.
Yeah.
That's awesome.
Look for go talk to Asher Tubman.
Okay, cool.
He's in room what is it, 415?
Okay, awesome.
Yeah. All right, cool. Well, let's get started. All right, so yesterday we covered a lot of stuff. I think everyone will agree we covered a lot of material. One thing that I think we need to cover a little bit, just to make sure, is to make sure that everybody's comfortable with it, is figuring out how long an antenna needs to be for a given frequency. So what we're going to do is we're going to start with that circle again, 300 F and lambda. Remember that this is in megahertz and this is in meters and the reason this is in megahertz is because this is the speed of light. We've gotten rid of the 10 to the sixth power because we're not looking at 300 million meters per second. So we just eliminated that 10 to the sixth. That's why we use megahertz at the bottom. So what we're going to do is we're going to look at a half wave antenna at 6 meters. So this is going to require us to do a couple of different things. First one we're going to have to do is we're going to have to understand what 6 meters means. So who's going to volunteer to do this? Somebody volunteer to do this.
6 meters means that
That's
the
6 meter band. Who's going to volunteer to do this?
that means that the wave, the one full cycle of the wave takes 6 meters to accomplish.
Correct. All right. So who's going to volunteer to be to do the math and tell me what to do? Come on, somebody do it.
300 divided by 6.
But we're not going to do that because what do we know about those about wavelengths? They are approximate. When they specify a band, it's the approximate wavelength. So what we're going to do is look at our frequency spectrum. And that's always the first place to start because those wavelengths that they give are approximate and we need to be pretty close. So we're going to go with exacting. So here's our band plan. I believe I sent a copy of this out to everyone. Hopefully you've all seen it.
Yes.
Okay. So, all right. So who's my volunteer? Oh, come on. Somebody volunteer.
I'll volunteer.
Okay, good. Okay. All right. So 6 meter band.
Uh-huh.
I brought it up pick a frequency that's in the 6-meter band.
52 megahertz.
52.0. Okay, that's our starting point. So we're going to go with 52 megahertz. Okay, 52 megahertz. Okay, what does our circle look like? 300 F lambda. All right. Where does the 52 megahertz go?
The F.
Yep. Okay, so we have 300, 52, and lambda. Cross out the lambda, and now we got to calculate 300 divided by 52.
Oh, let's see. 5.7.
Okay, so that could be important. And what are the units of that?
Meters.
Meters. Okay. And why is that so important? Because it's the quote 6-meter band, but what we just found out is that it's really not. The wavelength that we are looking for is 5.7 meters. So we're going to make a half wave antenna. So if a wavelength is 5.7 meters, how long is a half wave?
It would be like 2.67.
2.85.
Yeah.
Okay, so that's a half wave, 2.85 meters. Okay. Very important part, though. We need to multiply by 95% because the real world actually tends to shorten our antennas from what the theory says. So, dude, what does the calculator say? 95% of 2.85.
It's 2.7.
2.70 megahertz, or sorry, meters. 2.70 meters. Okay. The next thing we have to do is we're going to convert this to inches. It is 39.34 inches per meter. So multiply that by 39.34, if you would.
It's 106.5.
Okay. So at 52 megahertz, the proper length, the proper, well, according to the theory, the proper starting point for that antenna is 106 inches. So if you were making this antenna, this is practical stuff. If you were making this antenna, and this is a half-wave dipole looks like this. If it's a center-fed half-wave dipole. All right. So how long does each leg have to be when you go to cut your wire?
Half that
Half that. So about
for the wave.
53.25 inches. Okay.
Does that include the vertical part also?
This right here, that's feed
No.
line. That's the feed line.
Oh, okay.
That is not part of the radiating antenna. So now what's important here is this is the practical stuff. When you go to make your antenna, what would you start with? What do you think? For each leg, how long would you cut your wire?
Probably
56,
54 inches.
58.
I'd go 55, 56. And why is that?
Because you can always shorten it.
Yep, you can always trim pieces off the end. If you cut it too short and it resonates, if an antenna is too short, will its frequency be too higher or lower than you want it to be? Think of a tuba.
It's
Yeah.
inverse.
It's inverse. Think of a tuba. Tuba's low frequency. So if you end up cutting too short, your resonant frequency will be higher than you want it to be. And you can't easily add extra wire. I mean, you can. You could solder something to it, but then you have solder, and then that gets that makes it kind of rigid and it doesn't bend anymore. It's a lot easier to start a little bit too long and cut it shorter. All right. So now that's good job, by the way.
Question.
Yeah, go ahead.
I've seen a lot of guys fold over the wire and wrap it. Does
Yep.
that have any effect?
It doesn't really lengthen it. So yeah, I do that too. I usually
I
like,
mean to shorten it.
Um, yeah, yeah, it does. It shortens it a little bit. But now the thing is, so he's saying you take it and you can fold it over like that, and that will shorten it a little bit. Yeah, instead of snipping the end. Actually, what I usually do is I usually tie a knot in the end because I'm tying it to something. And all this stuff, it doesn't really affect the resonant frequency at all. The other thing you can do with it, if you want to make something a little longer, you can have an anchor point here and just let it dangle down. Ooh, waterproofing. That is a very good point because that feeds into our next section. We started talking about feed lines yesterday, and feed line, coaxial cable, twin lead, et cetera, and SWR. So if we have a feed line, and I'm going to draw a piece of coaxial cable and hopefully do it better than I did yesterday. Okay, so here's our cable. So we have our center conductor and we have our shield. And notice that we have multiple exposed surfaces, right? So we'll take a connector and we'll put it on here. It goes like this. It's, let's see, it'll look like that. And then something will capture the pin and it'll all be soldered up. Okay. What is the one thing that you think that could destroy a coaxial cable for which the metal is made of copper? The conductors are copper.
Moisture.
Moisture, yes, because what will moisture do to copper?
Corrode.
It will cause it to corrode. And then once it corrodes, what you end up with is something that isn't really very conductive anymore because it's now covered with an oxide. Oxides aren't nearly as good as the actual piece of metal, and yes, it will turn green. So what you end up with that at that point is you end up with um, typically a signal that is trying to pass through a connection that is not really solid anymore. And let's say that your cable now, well, this part is 50 ohms, right? This cable is a 50 ohm cable. Your antenna is about 50 ohms. That's pretty good. You've done a good job on it. You've done a little impedance matching, but in here, you've put a connector. And then there's a mating connector right here, and you didn't waterproof it. So what can happen at that point is that you get water intrusion into the cable. And remember that a cable is modeled as a capacitor and an inductor and another capacitor. Well, if you, for instance, add some resistance, that causes it to be lossy. And also, if you let's say infiltrate the center part of it with water, that can actually change what the capacitances are. If you change the capacitances, you change the impedance of the cable. So waterproofing is really, really important. So damaged cable can cause the SWR to jump all over the place. Remember, SWR is the quality of the match that you have. And numerically, so here's your cable, and here's another connector, and here's more cable. This is 50 ohms, and this is 50 ohms. And ideally, this connector is 50 ohms, and this is 50 ohms, and your antenna is 50 ohms. But let's say that something happens and this cable up here, because of water damage, becomes 120 ohms. You have a severe mismatch now, right? You have almost like a 3-to-1 mismatch right here, which will cause reflections in the cable, which will cause signals to bounce up and down the line. It could cause your power to fold back in at your transmitter. And what it really means is that you're not going to get nearly as much signal out of the antenna. And you're going to be heating your cable. Yep, you're going to be heating your cable. And what are a couple of ways to get water into coaxial cable?
To get it into or to keep it out?
No, well, how does it get in?
UV degradation of the
Yeah, that's a
coating.
really good one. UV, if this is out in the sun, some cable is not UV proof. What happens is that the material that it's made from will crack. Well, okay, if the jacket cracks, you have cracks that allow water to get in. The other one is if you have a connector and you haven't waterproofed the connector properly, and it's not a waterproof connector intrinsically, you have water getting in. And either way, the end result is the same. Something you just want to avoid if at all possible.
So do we shrink wrap the connectors?
So I have seen as many different ways to waterproof cable as you can imagine. Um, there are some cables that are direct burial. You could run it in conduit, but conduit can still get wet. Um, there are some cables that are direct burial, as they're called, which means you can, if you're putting it in the ground, it doesn't matter how wet it gets. If you run, for instance, if you think of your system as something equivalent to what cable TV would do, because what happens if you get a leaky cable TV system? Has anyone ever experienced that?
Lousy reception.
Yeah, your reception quality goes way down. And if anybody, if there's anything else outside, it can interfere because not only does it leak out, but stuff can leak in. So they have, I typically use like a rubber mastic. There's something called coax seal. Um, if you are going to be putting something that's going to be sitting outside, like you'll typically do like a self-sealing mastic and then electrical tape over it, and then maybe another layer of that mastic, and then maybe another layer of tape. Now, what's really important to note is that if you're going to do that, you're not going to get in and be repairing anything anytime soon. It is semi-permanent, and if you're going to take anything off, you have to cut it off. So tighten everything down, make sure all those solder connections are good before you do all that, because if it's not, you have to get in there, you got to start all over. Let's see.
I see a lot of guys smear it all with Vaseline. Does the Vaseline affect it at all?
I don't know. I mean, it's waterproofing, but I don't know how well it actually works. I
I know
mean,
that
they used to bury machinery in cosmoline, right? It kept all the water out for sure. So
Took a while to clean off.
that's a lot to clean off. Yeah, exactly. Okay, so what we're also going to show you now is connectors, 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 because a piece of cable without a connector doesn't do a lot of good. You have to be able to get your signal into and out of your cable, into and out of your equipment. So everybody see all of these? There are different kinds of connectors out there for different kinds of frequencies. The one that is on the center of the screen right now, this is known as a UHF connector. And oddly enough, UHF is only good up to about VHF. They are not waterproof, and they above about 200 megahertz, they tend to get a little bit they tend to get lossy. This, however, notice that this is like a double ring. This is called an N connector. N connectors are good into the many gigahertz. This is a male N connector. This is a female N connector. Male UHF, female UHF. Some of the smaller radios that you'll see at the bottom of these things, those are SMA connectors. SMA connectors are actually really very good. They're threaded connectors, and they are good up to many, many gigahertz of frequency. But they can't handle as much power. So, and that is true, Rob. Thank you. There are two different versions of N connectors. There's a 50 ohm and there's a 75 ohm N connector. So you have to you have to know which one you're getting when you're mating the two. Otherwise, you'll end up breaking something. Those UHF connectors that we use, those are the most common. They're called, again, UHF connectors, and these are not good for a UHF. That's the common term for it, UHF connector. This is usually an SO239 or a PL259. This is the male and this is the female version. That is most likely what you will see on a base station radio because they're good up to about 200 megahertz. If you get a UHF radio or a radio that does multiple frequencies, it might have multiple different output ports, and that will have an N connector on it. You cannot run a ton of power through an SMA connector because it's really quite small. If you want to run high power at UHF, you're going to use an N connector. Some types of cable that we use for 50 ohms. There are 75 ohm cables. That is very common in cable TV. You can use 75 ohm cable, especially because there's a ton of it surplus. If you're going to use surplus cable, what do you have to make sure of?
Make sure it's not degraded by
Make sure it's in good
UV
shape.
or
That's right.
lit.
Make sure it's in good shape. But I have put up lots of runs of coaxial hardline in my life. So, okay, so we can start with a cable that is small, RG174. This is radio gauge 174. This is small cable, very low power, but it's 50 ohms. The next one is RG58. Oh, is it radio? Yeah, I think it is radio guide. Thank you. RG58, that's also 50 ohms. RG8, actually 8X, that's also 50 ohms. This is RG8, and that is also 50 ohms. And then we can get even bigger. We can get all different kinds of sizes. Okay, so why would we pick one over any other one? This is 50 ohms, and this is also 50 ohms. Notice they're all 50 ohms, characteristic impedance. And that's because they are just scaled up versions of each other. So why would we pick any one cable over any other cable?
I would say either frequency or loss.
Okay, frequency.
And your power expectations.
Yeah, frequency and loss, power, other things. Cost, yep. Other things?
And the length you're going to run.
Correct. You have length because the longer it is, the more loss you have. Other things?
Convenience.
That's a good one. Other ones?
Yeah, type of run, where it's running.
Okay. How about hole sizes? Okay. Anything else? This is great.
As in drilling holes in the wall, or
as in drilling holes in walls.
Get a bigger drill.
Yeah. Any how about cost of connectors? A basic connector, and notice cost is there. So this might be $1 a foot. This might be 40 cents per foot. This up here on the upper right for hardline might be $12 per foot. 6-inch hardline could be $240, $250 a foot. And the connectors that you use are not your normal connectors. A connector for 1-inch hardline can cost $250 just for a connector. For 6-inch hardline, this might be $1,000 for just a connector. So why would you ever go with 6-inch hardline, for instance, or 1-inch hardline Hardline is a semi-rigid, semi-flexible stuff. The way that that's achieved is that it's actually like an articulated jacket instead of being like a braid. So the reason that you would ever do that is, let's say you're building a moon bounce station, for instance, or let's say you're putting up a commercial TV station where you're running, 20,000 watts or 100,000 watts. Well, you're going to end up going with something really big. It's also going to be probably running 600 feet up the side of a tower. So you have a very long run. You have a lot of loss potentially. Now, the other issue with hardline, of course, is if I build something out of hardline looks like this. It's just cable, except that the outside is heavy and the inside conductor might be, you know, 3/4 of an inch. That's copper. That's heavy too. This stuff is super heavy. So you have a choice of how to fill this with material to keep everything separated. What would you fill it with ideally? What do you think? To keep the to keep the weight down. Yeah.
Nitrogen.
Yeah, instead of something solid like plastic, because plastic's going to add a lot of extra weight, you would add nitrogen. Okay. How do you keep something pressure tight?
You have to have grommets on the outside sealed, and there's actually like a spiral uh, copper that holds that center core in place.
Yeah.
I had the privilege of putting in a TV station in Uganda, and we had to run 300 meters straight up to the needle.
Uh-huh.
And it was an 8-inch coax, nitrogen
Yep.
filled at 13 pounds pressure.
Yep. Oh, that also means that at the base you have to have a nitrogen tank that's connected to your jacket. So all the connections have to be pressure tight. And the reason you use nitrogen from a pressurized tank is to do what? Everyone?
Keep the water out.
Keep the water out. It's always about keeping the water out. And since it's not filled with a solid, it's filled with space, you have to fill it with something that's predictable to keep the water out. Everything's about keeping the water out. So most of us will never need to do this. But let's say that you work with a group that manages a repeater. And the repeater, if you're lucky enough, is on top of a 400-foot tall tower, right? Well, you're not going to use lousy coax to get up to the top of that 400-foot tower, because what would be the point? Most of your signal would be gone. And you're not going to put the repeater itself, all the hardware, 400 feet up the tower, because then if you have to do anything to it, somebody's got to climb 400 feet up the tower. So practically speaking, you're going to have a long cable run. So this is actually what a lot of commercial installations do. And again, why a lot of hams do this kind of thing for a living and vice versa, because there's a lot of overlap. And there's a lot of mobile radio systems out there. There's a lot of opportunity for jobs in this area. RF, a lot of RF engineers and technicians are retiring. So this is definitely a growth area right now. Okay, moving on. There's one thing that I wanted to bring up, yes, which I did not remember yesterday. What is this thing called?
Diode.
That is a diode. What is a diode again?
Keeps DC current flowing only in one direction.
Only in one direction, in the direction of the arrow. Okay. Plus and minus. This is the cathode. This is the anode. Cations, anions, cathode, anode. If you see one of these in physical form, not in a schematic form, but in a physical form, you can tell which end is which because the cathode has a band on the end. Think of it as a sideways negative sign. So that's the negative end. It has a stripe on the negative side. Okay, are there any questions from yesterday before we get into today? Because we got a lot of material to cover today. I would like to point out that yesterday we basically made it through the equivalent of about page 55 in the book. And we're going to be looking at the book more today because we're just going to be working through it. And there's a lot of stuff that you don't really have to, we don't really have to do a whole lot of explanation using the whiteboard, but we're going to be bouncing back and forth a little bit. So one thing with regard to that is SWR. Okay. So we got to the point of doing standing wave ratio yesterday. And the easiest way to think of standing wave ratio is, for instance, we have a 50 ohm impedance matched to a something or other that has 300 ohms impedance. This right here, this is 6, this is 1. This is a standing wave ratio of 6:1. That is a very, very bad match. Most of the power does not transfer out. Similarly, we could have a 10 ohm impedance here. Well, because it's a ratio, we take the ratio of the bigger one to the smaller one. This would be 5:1. So we're looking at kind of the absolute value. We're not using fractions or anything like that. All we need to know is that it's a mismatch. That is a 5:1 mismatch. It's bad. SWR is not related to frequency. It is related to impedance, and that's all. Now,
And it doesn't matter which direction the mismatch is.
nope. A poor match is a poor match. I mean, yes, it depends a little bit as to whether or not a signal that bounces back is going to be in phase or out of phase. Reflected above or below the zero line. But ultimately, it doesn't really matter. A bad match is a bad match. So if you have a 1:1 SWR, that would be like getting 50 ohm coax and connectors, and then 50 ohm coax on the other side. That is a perfect match. That is perfect. Okay. Then if you start to get 2:1, this is okay. You can get away with it. If you have a 4:1, this is what we would really consider a mismatch. Now, a lot of HF radios today include an antenna tuner, which is an impedance matching network. So a radio, typically an HF radio, will look for a 50 ohm impedance. So here's your 50 ohm cable and 50 ohm antenna. And let's say that something happens and instead of being 50 ohms, it's 125 ohms. What would that mismatch be? What is that SWR?
2.5 to 1.
2.5 to 1. That's not really great. Most of the antenna matching systems that are built into radios today have a maximum impedance match of 3:1. So that would typically be able to match automatically. You press a button and it goes through and switches in capacitors and inductors, and it will be able to match that. If you had let's say instead of 125 ohms, it was 250 ohms. That would be a 5:1 mismatch, and your internal tuner would have a lot of trouble matching that, which is why a lot of people then go and they get an external tuner and use it outside, whether it's automatic or otherwise. Okay, one thing that can happen is if you have a mismatch of, let's say, 4:1, this can actually be hidden to a certain degree. We can measure our SWR by means of forward and reflected power using something called a directional wattmeter. So we have our forward power and reflected power measured simultaneously by the direction they're traveling through the system. And if we have zero reflected power, that means that when we hit that load, which is the antenna, we have zero reflected power, right? Well, if we have zero reflected power, all of it must be going out, right? Which means we have a perfect one-to-one match. But here's the other question. Let us say that we have, instead of a perfect piece of cable, we have a piece of really lossy cable. So, and you don't have a perfect match. But what happens in the lossy cable? Power loss turns into what?
Heat.
Heat. Okay, so power loss turns into heat. Does it ever make it back to the point where it can be measured by the reflected meter?
No.
So what does it look like your SWR is?
It looks good.
It looks good, yeah. So lossy cable can mask an actual problem that you have. Okay, another one.
What was the name of the meter that we were using?
This is a
for
directional
the
watt.
reflective?
This is a directional watt meter. This is a directional watt meter. And most SWR meters use that. They measure power going in each direction along the cable. Okay. Let's see. You should always put your SWR or watt meter between the transmitter and the antenna, obviously. You should always put it as close to the transmitter as possible because you really want to know what's happening on in the outside world. So you really want to see what's happening way out here. Okay, a dummy load. All right, so I brought up yesterday that we have this thing called a VAT. What is that, everyone?
Inductor.
Inductor. Okay, now, because it's a piece of wire, it has resistance, but it also has inductance. The inductance feeds into something called reactance, which feeds into impedance. And this, you'll remember, maybe, is 2 pi FL. What do you notice is that term right there? What's that F term?
Frequency.
Frequency. Your impedance, if you draw it on a graph, here's your resistance, here's your reactance, is R plus JX. And again, because they're perpendicular to each other, that's how we indicate that they're perpendicular. So if I have a resistor that is 50 ohms, and I put that at the end of a cable, that's 50 ohms. What will my impedance be at that point? What will my match be?
Should
My
be 1 to 1.
SWR? That's a perfect one-to-one SWR. But what if I have a coil? Because that is how a lot of resistive wires are made. They're coiled up. Uh-oh. Well, that now has L. Uh-oh. And what does that value do? It changes with frequency, which means that this direction gets bigger and smaller depending on frequency. Well, this resistance part is still 50 ohms, but the reactance goes up and down depending on frequency. So at one frequency, we might have 62 ohms. At DC, we have 50 ohms. At another frequency, we have 74 ohms. How good of a test device is a device that changes all the time? It's a very poor device. Yeah. This is supposed to be a 50 ohm. It's called a dummy load. A dummy load is a device that replaces an antenna and is used to do off-air testing. So if it is designed for 50 ohms. Well, you would hope that it is always 50 ohms, right? But if we build it out of the most commonly made thing, we find that a wire wound resistor that's 50 ohms, our impedance is not 50 ohms, and it makes a terrible device. So what we end up doing in order to achieve this is we buy a special resistor that can be made of carbon, but typically they don't handle that much power. We buy a special resistor that does this. And why would it do that where it doesn't ever complete a loop?
So it's not an inductor.
That's right. It doesn't have a full coil of wire. This is called a non-inductive wire wound resistor. And that is at the core. They're a little more expensive, but that's at the core of most high-powered dummy loads, which are test devices. Okay, any questions on that before we move on?
Are the old paint can with resistors any good or no?
Oh yeah, Heathkit Cantena. I have one. If anyone's familiar with a Cantena, it's a paint can that looks like this, which you then fill with oil to a certain depth, and you have a connector up top, and it goes down, and there's a big resistor in the oil bath. These are good dummy loads that will run up to 1,000 watts for like 15 minutes before it gets too warm. The one concern is you have to look and see how it was made, and hopefully you can find the person who did it who can tell you what that oil is. Mineral oil is okay. Transformer oil could be okay, but depending on when it was made, it could have PCBs in it. And those have been around for 60 years, those Cantenas. So I built one. I built mine myself. It has mineral oil in it. Yes, I got a lot of weird looks at the drugstore. If you're old enough, you know why. Okay. Now we're on to page 57, and we're on to amateur radio signals. Okay. So amateur radio signals. Okay, we're going to start with this. What is this? Everyone, what is that?
Sine wave.
A sine wave. And what are some properties of that sine wave? It has a what?
Frequency.
It has a frequency. What else?
A speed.
Wavelength.
Somebody said it has an amplitude. It has a wavelength. What else?
A speed.
It has a velocity. Yeah. What else? Yep. It has a period. What else? It has
It's
a
not
phase.
uniform.
It has a phase. Okay. So it has all those cool things that describe it. Now, if I don't change anything, what does a tone simply tell me? It tells me that there's a tone there. Well, that's not a lot of information, right? So what are some things that I can do to make this more interesting and change it? What can I modify? I can modify the amplitude. I can modify the frequency. I can modify the phase. We're going to use an angle. I can modify presence or absence. I can do a whole bunch of things, right? So what we're going to do is say that this is an unmodulated carrier. It's an unmodulated wave. It is really boring. It just tells you that there's a tone. But what I can do with it is I can do this. I can change the amplitude. Well, the act of changing something to make it contain information is called modulation. This is called amplitude modulation. Everyone's heard of AM. I could also keep the amplitude the same, but I could change the frequency by doing this. I'm changing the frequency. That would be frequency modulation. I could also keep everything looking like this, and I could suddenly have a jump from this point up to here, and then have another one where it's like here, and then have a jump where it goes like this. It jumps to another point in its angle. That would be a change in phase. That would be phase modulation, because when we're listening to this, somebody, if you can build a tool that actually can decode what this is doing, that would be a demodulator. So the act of changing it is known as modulation. The act of getting rid of that change is called demodulation. So you can recover the original signal. You put a modulator and a demodulator together, you get MODEM, which is a modem. That's what a modem is, a modulator demodulator. And depending on how the demodulator is built, it can undo what the modulator has done. We could also, yes, recovering the intelligence. Here we go. We could also just take a signal and do this with it and turn it off and turn it back on. Anyone know what that's called?
Your CW or your Morse code?
Yep, that's CW. That is Morse code. So all of these different things that you can do put information onto a wave that can then be recovered. You can get the information back out. So most voice repeaters, we're on page 57. Most voice repeaters use phase modulation or frequency modulation. There's something called packet radio. Packet radio is basically digital communications over FM. So instead of encoding voice, we encode digital communications, which are ones and zeros sent by a computer. Yep, APRS uses packet, and yep, lots of other amplitude modulations. And okay, so if you have two different phase changes, for instance, available, that would be binary phase shift keying. If you have four different ones, that would be quadrature phase shift keying. If you have 8 different ones, that would actually just be called, instead of octagonal, it's 8 PSK. There are lots of different ways of doing this. For doing single sideband, now what we're going to have to do to understand this, we're now moving from the time domain. This is the time domain. We're looking at amplitude or a signal versus time. But now we're going to have to shift back to a different view. And the different view is a part of this. Nope, that's not it. Darn it. I grabbed the wrong thing. The different view is a part of this. There we go. Okay, everybody, what is this right here again? This has a name.
Band plan?
Nope, this is the electromagnetic spectrum. Okay, so when we look at the spectrum, this is a view of frequencies, amplitude versus frequency, right? The amplitude is up and down, and the frequency goes side to side. There's a tool called a spectrum analyzer, which allows us to look at a spectral view of everything that exists in this spectrum. Notice all the way on the right-hand side, we have an actual spectrum, right? Actual color spectrum, because that form of light is really just colors. We can use a prism to break up that light, which looks like white light, and see the different colors. Similarly, we can do the same thing with radio. let's say that we use let's say we are wearing rose-colored glasses, right? We're looking at the world through rose-colored glasses. Everything looks kind of red because it's filtering out everything else. Essentially, what a radio what a radio receiver is a filter for just one very narrow piece of spectrum that allows us to visualize and hear what's on there and recapture the information. So we're going to be basically looking at this from a spectral viewpoint. And this is called the frequency domain. So when we look at a frequency domain, we look at amplitude versus frequency. And this goes from 0 hertz all the way up to infinity. We could take a small piece of it, but this is really, it really extends from 0 frequency, 0 hertz, all the way up to infinity. So we are going to take a look at a small piece of it, and we're going to say this is our frequency of interest. FC, that's our center frequency. This is what our radio dial is tuned to. That's our center frequency. So when we do this and we send amplitude modulation, you remember amplitude modulation looks like this. We get something bigger and smaller. Amplitude modulation actually looks like this on the frequency spectrum. It has an upper sideband and a lower sideband. When we do this, those are actually mirror images of each other. But if we have a total of 100 watts to put out, we might be putting, let's say, 40 watts into this carrier, which is a marker, and then 30 watts into here and 30 watts into here. Well, okay, if this is a marker and all it does is indicate a frequency, do we really need it there? If our receiver is smart enough to be able to put it back in when it gets there? No. So this is AM. AM takes up about 6 kilohertz of bandwidth for a human voice. It fills up about 6 kilohertz or 6,000 hertz wide. And the reason being that people's voices typically are between 0 and 3,000 hertz. So it goes from 0 to 3,000 above and 0 to 3,000 below. Well, this is actually really important because the lower sideband and the upper sideband are actually just mirror images of each other. If they don't contain unique information, do we need to send both of them?
No, either one would work. One's
Either
just
one
converted.
works. Okay. So in the mid 1950s, it was determined that, you know, using some selective filtering before we actually send this stuff, well, we could suppress the carrier. So what we're going to do is we're going to knock out this carrier, which wastes 40 watts of power. And because upper and lower sideband are mirror images of each other, well, we can do this. So instead of now using, we're going to get rid of that. Instead of using 100 watts, we get the same effect out of 30 watts. That's pretty good, right? Because in reality, we still have a 100-watt transmitter. So we could put all 100 watts into here, which means that we get a bigger signal. We get better coverage. This is known as single sideband. And instead of 6 kilohertz, it's now 3 kilohertz wide. So in addition to being more efficient, we can actually put more signals into the same place because remember that spectrum space bandwidth is a resource. If we have signals that overlap with each other, they don't really get through very well. So by doing this, by going to single sideband, we could choose upper or lower sideband. And what that allows us to do is save power and be more efficient with the bandwidth.
Yep, which would cut down half of the bandwidth that you would use, right?
Yeah. And you don't have all these,
That's
you don't
great.
have all these annoying heterodynes, which are those when you tune an AM radio or an FM, sorry, a single sideband radio around, if it's over on AM, you get all of these marker frequencies, which are just annoying pitches, just whistle pitches.
Right.
Those are the heterodynes that mark frequencies in AM. An AM receiver is a simpler receiver, and because of that, it can be, easier to build, but it's also wasteful as far as power and bandwidth. So single sideband requires about 2.4 kilohertz typical in bandwidth for filtering. So a single sideband signal, you can get away with a 2400 hertz filter. A lot narrower. Now, there are other modes that we can do. For instance, I'm going to erase that, and we're going to draw another signal that looks like this. And this is CW. This has a bandwidth typically of about 150 hertz. That's Morse code. So now that we're looking at bandwidths, you could use a 500 hertz filter very well to hear just the signal that you want and ignore all the other ones, which is great because they don't have to fill your ears. The other thing we can do is that we're going to spread out this spectrum a little bit, and we're going to draw a single sideband signal, and we're going to make it blue. So here's our single sideband signal. That's 2500 let's say 2500 hertz wide. We're going to draw a bunch of Morse code signals, and they're going to be lavender. And they're actually spaced out pretty well. What's the big advantage of this?
The CW will punch through where, because it's just off on tone.
And how many?
Punch through easier, correct?
And
you
how
could fit a ton more in there.
Yeah, and how many signals can we put in one place that one single sideband signal could handle? Right? Much better use of the spectrum. It doesn't carry as much information. So this is something that is important for everybody to remember. Typically, the more information that you put onto a signal that you use to modulate it the more space it takes up. Yep. Modulation leads to use of space, use of bandwidth. So if you have a signal that is full of information, right? And yes, this is from Claude Shannon. If you have a signal that's full of information, it's going to take up space. It's going to take up more space than a signal that is full of not very much information, which means that your data rate will go up. So let's say that you're doing Wi-Fi. What's everybody's Wi-Fi speed? At my house, it's about 300 megabits per second. So I then take that, a bit per second, that's a thing per second, right? I got to send the data. That would take up about 300 megahertz of space. Where am I going to find that on our frequency spectrum chart? Where is that available? A single signal can take up that much room?
You got to go to higher frequencies.
Here we go.
In the band.
Here we go. And that is why we are up in the gigahertz range, because 300 megahertz of bandwidth, 3 gigs, 2 gigs, 3 gigs, 5 gigs, you can actually do that. You can actually get away with it. Whereas down here, there's nowhere to put a 300 megahertz wide signal. Again, it's, available space on that chart. Okay. So there are other.
Would that also help us identify, like when you have the waterfall display?
Yes.
Would that would help us determine what type of signal was being broadcast by the width of the pattern?
That's a big part of it. I'm going to actually bring that up at our next break. So there are other signals. There's something called PSK, which is phase shift keying. PSK 31 actually takes up about 31 hertz. Really, really tiny, even smaller than a Morse code signal. Okay, so what's the advantage of these really narrow bandwidth signals that don't carry a lot of information? Well, I'm going to take a signal and I'm going to say, here's my single sideband bandwidth. Okay, well, everybody uses single sideband. And then I'm also going to take my Morse code signal, which is about this wide. All right, and I'm going to put walls on that space. And here we go. Here are the walls on that space. Okay. Now I have a bucket of water. All right, so here's my bucket of water. And it is filled with water up to here. And now I'm going to use that bucket of water and fill up the single sideband bucket. When I do that, it's going to get up to about here. How about when I fill the Morse code bucket? It's going to fill that
jump over the top.
way up to here. Yeah, it's going to
Yeah.
go. I actually have to extend the walls. It's going to go like way up to here. This actually represents something physical, because the amount of water I have available in that bucket represents the amount of transmitter power I have available. It is limited. So what does that really mean? If I have a deeper available water bucket, uh-oh, somebody drew something there.
The narrower the band, the more power you get up through there then.
Yes, and this is something known as power spectral density. And what it really means is that now, if I look at any given frequency, I have more power dumped in at that particular frequency than this one does. Which means that, let's say I look at this little swath and I have the equivalent of 1 dBm right there. And I look at this same width swath on this one and I have 24 dBm. And now I do that same thing that we did yesterday, which is I draw our entire signal from one end of a chain to the other, one end of a path, where I have a transmitter here and cable and an antenna, and then it goes through space, and then another antenna and another cable and a receiver. Which one has the advantage in the first place? Which of those signals? Is it single sideband or is it Morse code?
Morse code.
Because it's deeper in the first place. I have a higher power spectral density to get basically wiped out. This one, single sideband, because the power level is lower, will be the first one to go when conditions get bad. So that is why a lot of narrow band modes are the last things to stop working. That's why, for the most part, if we're doing something like moon bounce, where you need, you have 250 decibels of path loss, that's why we almost never use single sideband, because you would spread out your signal so wide that you're already killing it before it even goes through the path. That's why we use very narrow bandwidths. If you're really close to somebody, it turns out that FM actually is a bandwidth hog. But what do we use FM for?
Really close
Transmitting
communication.
data, right?
Yeah, FM is great because it's like noiseless and you don't get static and right. Well, here's CW and here's SSB and here is FM. FM is 10 to 15 kilohertz wide. CW is 150 hertz wide. An FM signal is 100 times more, it fills up 100 times more space. But it's also got a lot more clarity and people can talk. There's a lot more information being carried from point to point. So in order to generate this, um, in order to decode an AM receiver is really simple. An FM receiver uses something called a discriminator. It's a very special little box. And that actually uses remember somebody said yesterday that they were under deviating or over deviating because FM is frequency modulation. Your frequency starts at one particular center point, and when you talk into it, it causes the frequency to spread around. So here's our center frequency. When you talk, it causes the frequency to bounce over here and then bounce over here and bounce over here and bounce over here and bounce over here in the pattern of a sine wave. So it fills up the entire space of frequencies. The amount of deviation you have determines how wide it gets. So what happens if you are deviating all the way out to here, for instance, and the receiver has a bandwidth that looks like this? What's going to happen when somebody tries to listen to it?
The excess will get lost. It'll
The
be
access gets
distorted.
lost, but the access is part of what your voice is doing. This stuff gets lost. So what happens to your voice? It sounds all distorted because a part of the signal that makes up your voice is now gone. Yeah, that would basically be it's over deviation, over modulation. Similarly, you could be under deviating, under modulating, in which case you'd sound really quiet. People would have a hard time hearing you. So when that happens, what you do is you get closer to the microphone so that you make it spread out further. All
But
right.
that's why FM's clear though, because it's based on the spacing of the waves together more so than the width of the wave.
Well, and
So you
FM
can
is
discriminate the excess
and
and still
FM
get the same.
FM is also really clear because as this happens, what ends up happening here is that the signal, let's say that you get a static crash, right? We get lots of static crashes. What that does is that it increases it increases the amplitude across all frequencies. That's what static does, which essentially takes this signal and builds it up higher and higher and higher. But it does the same at all frequencies, no matter what the frequency is over time. And when this gets into your receiver, it doesn't change the actual frequency. And then your receiver does this and cuts off the top and bottom, preserving the frequency and turning it back into a sine wave. Yeah, that Army video was pretty cool, wasn't it?
Yes, that was amazing. That really, really helped understand all that.
I was amazed that it was, like I said, it's the best explanation of FM that I've ever seen. So
yeah, I would have to agree. That was very, very informative there.
all right, everybody ready for a 5-minute break?
Sure.
Okay, if somebody has that link and wants to put it out in the chat, they should go ahead and do that.
Yeah, I would highly suggest everybody go watch that, when you get time.
No. You want to come in and lie down? No, lie down, Lucky. Lie down.
All right, can everybody hear that?
Yes.
Okay. Any idea what that is?
That would be CW.
Okay, but what is actually being sent?
Just your dots and dashes.
No. These are beacons. These are propagation beacons. Let's grab one. From Zael 3 TEN RE66 half wave vertical $50 So that's a beacon, a propagation beacon from New Zealand that's just transmitting its signal over and over and over and over. If you can hear it, that means that there's propagation between you and New Zealand.
So it's just kind of for testing who you can hear and in theory talk to. Is that the
Yep.
purpose of those?
If you can hear a propagation beacon coming in, that means that there's propagation between you and there.
Oh.
K5RWK/B EM12 PX and sometimes they'll drop down in power.
To see if you can still receive.
Yep. To see where it
Cool.
fades away.
Are there designated frequencies for those beacons?
Yes. Especially on 10 meters. This whole 28,200 to 28,300 is exclusively for propagation beacons.
Okay.
28 meters, 28 megahertz is a really wide band. And as you can see, we're at the top of the sunspot cycle because there are a bazillion 10-meter beacons. During the bottom part of the sunspot cycle, this band would be completely empty. It's really quite shocking.
So were you decoding that in your head as you were doing it, or
Yeah,
you have a decoder that's telling you what's being said?
Of course I can decode it in my head. I've been doing Morse code for 40 years.
I figured as much.
It's a second language to you now.
It is. K0. K0 KWC beacon. EM27, which is like Missouri.
So those are all beacons. Now, what part of the band is actually people using CW? Is there anybody active right now?
CW is at the lower end.
Lower end.
Yep. Oh, and there's a pileup. A lot of people calling at the same time. So this is a good chance to talk about selectivity and bandwidths and stuff like that. I'm going to mute this for a minute so I can hear myself think. Okay, so I want to make sure that we're staying on track. We're going to stop share and okay, single sideband, blah, 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 blah. Bandwidths, okay. An electronic keyer, all of those are being sent with an electronic keyer most likely. Okay, so digital modes. And for this, I'm just going to stop my share and start another share, which is the book. Okay, digital modes. Digital is ones and zeros, computers talking to each other, devices talking to each other. The nice thing about a digital mode is that if I said, okay, let's see, somebody pick a number between 1 and 100. Ready? Tell me when you got it. Somebody do it.
77.
Okay. How many different numbers are there between 1 and 100 by ones? There's 100 numbers, right? Yeah. If I pick 76, is that accurate or not? Would I be right? No. I'd be off by a little bit. I'm close, but I'm off by a little bit. So how about if I said pick a number between 0 and 1 by ones?
You're either right or you're wrong.
You're either right or you're wrong. Yeah. So let's say that the number, let's say that what I thought was closer to 0 than 1. Well, that's a 0, right? Again, it's either right or wrong. That's the benefit of digital. The fact that there's no gray area. Digital's either right or wrong. And that's why we use digital communications everywhere we use it, because if you have noise gets in the way of your ability to discern between things, right? If I let's say you picked 77 and for a moment there was some noise and it made me think that it was 82, right? There's no way I could figure out that it was 77. There's no way. But let's say that it was either 0 or 1 and there was a little bit of noise and it made it, instead of 0, made it come out as like 0.4. 0.4 is closer to 0. So it's a lot more tolerant to things that could screw up a signal. Packet radio, IEEE 802.11, that's also known as Wi-Fi. That's the protocol for Wi-Fi. And FT8, those are all digital modes. Packet radio is information that is sent via FM, typically over repeaters or digipeaters. And it contains where it's coming from, where it's going, automatic repeat request, because when it gets from one end to another, it's a computer that's figuring it out. Computer's running software. If a computer looks at it and says, I don't know what the heck this was, I can't figure it out, it'll say automatically, it'll send a signal back that says, send it again. I can't get that. A checksum. So let's say that I have a signal that is 111, right? That's our binary signal, 111. And if I had an odd number, I add an extra bit. I add an extra digit. If I had an odd number, I add a one. And if I have an even number, I add a zero. So I got 111. There's three ones. So I would add a fourth one. 1111. So if at some point I got 1110 because there was noise on the channel, well, I would know that I had a mistake because that's not even possible. My computer program could figure that out. That's called error detection. ARQ is an error correction method where it says I tried, I detected, I tried to fix it, but I couldn't. Please send it again. That's automatic repeat request, or ARQ. APRS is the automated packet reporting system. And essentially, it's a radio plus a GPS receiver where the GPS information is placed into digital packets indicating where the transmitter is. As it moves, what's cool about it is that it is then placed onto a map using data from the signal. So for instance, if I go to AP, aprs.fi, all that information is placed up at an internet-based server, which is in Finland, and everyone who is blurting out information packets is then shown on a map because there's locations associated with it. So if somebody's driving a car and they have an APRS transmitter on board, it can show that they're in a car, and it can show like there's a car, how fast they're going, where they went, and stuff like that. On long trips, it can be a lot of fun. It can also be used for tracking balloons, high altitude balloons that are flying around at 40,000 feet, for instance. People do a lot of that. It's also used for rocketry, for telemetry information, cool stuff like that.
AIS on ships.
Yeah, too. Okay. APRS. The only thing with APRS is that it has to be able to, the signal that it sends out has to be able to be received by something over the air. So real-time tactical information. So GPS position data, text messages, you can actually send text over packet and over APRS, and weather. PSK stands for phase shift keying. DMR, this is digital mobile radio. This is a system by which normally we would talk over most repeaters using analog radio. It's still FM, but it's analog. So it basically is, you know, direct voice to how far the frequency shifts. DMR essentially is a digital mode where your voice is digitized and used to split a channel in half. And there's a group A and a group B, and they can actually operate both of them at the same time without either one hearing the other. The benefit of that is that it essentially doubles the amount of information that a repeater station can transmit. And that's known as digital mobile radio. WSJTX. Okay, WSJTX is a suite of tools, the most popular of which is FT8, but it was basically designed by Joe Taylor. Joe Taylor is a ham radio operator, K1JT, who's also a Nobel Prize winning astrophysicist. And he really likes Earth, Moon, Earth. And he said, I want to create a mode that allows people with more modest antennas to do moon bounce signals off the moon and talk to other people because it's there, right? If it's there, you got to try to bounce signals off of it. So he created a mode called JT9 and JT65, which has then morphed into FT8. It's used for Earth, Moon, Earth. It's used for weak signals. There's also something called meteor scatter, which we talked about a little yesterday. WSJT, his entire suite of digital communications tools, runs all of those things. FT8, we saw a map yesterday, which showed what the propagation looks like from point to point, and it's populated by something called PSK Reporter. And for those of you who were not here during that moment, this is what PSK Reporter looks like. This is an internet-based tool that aggregates all of the reports that have been received by computers that are using FT8. So the nice thing about this is that people are sending out information, and other people who might even be asleep or might not even be at their equipment, they've left their receivers on, can indicate where their signal is getting to on the earth, send out a report, and put it on a big map. This is a great propagation tool for being able to see what the band is doing at any given time. And that was made possible by WSJTX and all of the different modes that it supports. Okay. Amateur radio mesh. So, because hams are allowed to modify equipment to do pretty much whatever we want, so long as it's legal, one of the things that we can do is that we can get, for instance, ubiquity routers and other hardware that is based in Wi-Fi. We can shift the frequencies a little bit, we can boost the power, and we can also modify the firmware so that it behaves the way we want and do stuff like being able to do long distance Wi-Fi over the airwaves, covering like 30 miles using a microwave dish. That's actually something called Arden. We do that a lot. It's similar to Meshtastic, except that it's a form of mesh, which is a self-healing communications methods. So there we go, Jude. Exactly. You have lots of mesh nodes. So Arden, AREDN, is something to look at. It's the Amateur Radio Emergency Data Network, and it is basically a practical real-time application of amateur radio mesh. So an alternative digital communications method, for instance, for getting radio signals from the Willamette Valley out to Florence in case something happens, there's an earthquake and the internet goes down. And because it's ham radio, you can't do you don't want to do anything private on it, but it can be really useful for getting general information out from point to point. And it's digital and it's Wi-Fi, which means it can do a lot of data really fast. Okay, safety, safety, safety. So we have electrical current. Electrical current flowing through you is a bad thing, right? Can disrupt your heart, can destroy your cells, and can heat your tissue. Just basically, if you have let's say an amplifier, some people will disable the interlocks. Those typically will run at 3,000 volts internally. Bad idea. 3,000 volts DC will kill you very quickly. Even 120 volts will kill you very quickly. So electrical safety is a big thing. There are 3 wires in the United States in your wall socket. There's black, white, and green. The hot wire is the black wire. White is neutral. The green is ground. Ground, again, is a reference point for 0 volts. It's a safety ground, which is interesting because it's different from an RF ground, which we will get to. How do you avoid electrical shock? Mechanical interlocks. Like I said, every so often somebody gets zapped by 3,000 volts DC and they usually die from it. Common safety ground and 3-wire cords and plugs. If you live in an old house and you don't have a grounded plug, for instance, you can always modify it and add a ground plug to it. Fuses. What's the purpose of a fuse? In case you have a current overload, the fuse will be a sacrificial element and protect your equipment. It will not protect you. That is a different thing. That is called a ground fault circuit interrupter. And it's the thing in your bathroom that if you drop your hairdryer in the sink full of water, it will keep you from getting electrocuted. Again, that's a different thing. Where should a fuse or circuit breaker be? In the hot line only, in series with the hot conductor. Why should you never replace a small fuse with a bigger, higher rated fuse? Because somebody designed that circuit. And if the fuses keep blowing, it's because something's wrong, not because the fuse needs to be changed and made bigger. So you can burn down your house that way. Power supply after turning it off. Power supplies have big capacitors. Capacitors operate as filters because they store charge. They can get rid of ripple, which is good, except that if they don't have a discharge resistor installed, when you turn off the power supply and you stick your finger in, you might get a nice shock because the power supply capacitors are still charged up. Has anyone ever worked on an old television? Like with a tube?
Yes.
Okay.
Yes.
How many volts could be stored on that TV tube?
Oh my God, it's high in kilovolts or something, isn't it?
25,000 volts. Yes. It
Yeah.
functions because it's a vacuum filled capacitor, basically. And if you try working on an old TV, if you don't discharge the tube first, you can get a really nasty shock.
Oh my, yes.
It sounds like you've gotten it before.
No, no, but I've seen the arc when you even get close to it.
Yeah.
You know, when you're grounding it out.
Well, yeah. Somebody mentioned cathode ray tube. That's exactly what's in an old school TV. So
Yep.
basically, anytime you have an electron accelerating tube, you get really big voltages. Safety hazard
Everybody's
of
rubbed their hand across the front of the tube and felt that static.
yes,
Right?
yes.
The old
And,
TVs.
and to think if you just rub your feet across the
Yeah.
carpet, you get a 20,000 volt. Yes, you get a 20,000 volt shock out of that. It's very low current.
Low, yeah. Very
Yeah,
low. Yeah, very low current.
very
Yeah.
low current, but it hurts. A TV has a lot more electrons in it, and it will make you it will really smart. 12 volt storage battery. 12-volt storage batteries are lead acid chemistry. And if you overcharge or completely discharge a storage battery like a lead acid battery, it can generate hydrogen gas. So if you create a spark near hydrogen gas, you can blow up your battery. The explosion itself might not hurt you too much, but if it happens to damage the battery and you get a shower of hydrochloric acid out of the battery, well, that can be bad. So that's why you want to avoid damaging a 12-volt storage battery. Notice overheating or outgassing. Sorry, I did say hydrochloric, didn't I? No, it's sulfuric acid. Sorry about that. You get a shower of sulfuric acid. And lithium batteries are scary as well, yes, because they tend
No
to
way to put
self-ignite.
out no way to put out the fire.
Yeah, you can't put out a metal fire. So yeah, sulfuric acid and lead. So you get hydrogen explosion showering you with sulfuric acid. Not a good thing. Antenna and tower safety. When you're putting up an antenna tower, watch out for electrical lines. You have to stay at least 10 feet away from power lines to make sure that when something falls, it doesn't come anywhere closer than 10 feet. Any closer than that, and you can actually develop an arc, and you do not want to do that. Most overhead power lines in neighborhoods are 12 or 13,000 volts. And they seem so quiet and calm most of the time, right? 12 to 13,000 volts. I was actually once at a Hamfest in Dayton, Ohio, where they had 7,200 volts and they brought it into the building to do a demonstration. And they had a bucket of water that was not grounded. And they took a piece of 1-inch thick sisal rope and they got it a little bit wet and put one end in the bucket of water, and the other end they threw up on a 7,200 volt power line, and it disappeared from view. So, yeah, electrical power
Yeah,
lines.
and you do not have to touch those to get contact, they do create
Correct.
a jumping
Correct. They
spark.
will arc. They will arc.
Yes.
They can arc quite far. So,
Yeah,
um,
I saw 3 geese get killed. They flew down between the high tension wires, and they didn't touch them. They just flew between them, and it jumped out and killed 3 of them. The
and
flock of geese that landed.
and some of those, and you may notice that some of the higher voltage power lines are even further apart, and that's because they can carry 765,000 volts, 1,000,000 volts.
Right.
So long as they're separated, actually that was one of the reasons that California condors were having a lot of issues in California because their wingspan was so big that they'd fly between 2 power lines and get electrocuted and die. So, um, so minimum safe distance, so that if part of it falls or any part of it falls, or you're up there 10 feet away at the closest approach. Why should you avoid attaching an antenna to a utility pole? First of all, it's not yours. Secondly, if it's got high voltage lines on it, well, in addition to being incredibly dangerous, there's there's a chance that it'll make a considerable amount of RF noise, so it's really not a good thing to do anyway. Has anyone ever gotten an RF burn? Anybody?
Yeah, I have. I've
Okay.
touched the antennas while they were broadcasting.
Yes. Well,
It's not severe, but
an RF burn it feels like heat, except that it'll make a pinhole in your skin. And essentially, because it's a very high, very, very, very high frequency, um, it will cause a nasty feeling burn on your finger, on your lip. I once got one on my lip when I leaned too close to a microphone while I was transmitting. So that's why you never touch an antenna during transmission. When climbing a tower, you always wear all your safety gear. You should never ever climb a tower without a helper. Um, when using a crank-up tower, never climb it unless locking devices are installed or it's totally retracted, because you don't want it to suddenly retract while you're on it. We use a safety wire through turnbuckles. Turnbuckles are used to tension guy lines. Those are the three cables in a triangular pattern that hold a tower up and keep it from swaying from side to side. Wind will tend to loosen turnbuckles, so we put a wire through it to keep it from loosening. You follow local electrical codes when putting up a tower. When you're doing grounding, each leg of the tower gets an 8-foot ground rod pounded into the ground, and then you connect them to the tower and to each other. You want lightning to have every chance possible to get into the ground. You want to install short and direct wires. You also want to avoid sharp bends when doing lightning protection. You want to do slow, gentle curves. Why should you never solder anything if you're doing lightning protection?
Lightning melts solder.
Lightning will melt the solder. Yes. So you want to use mechanical connections, either that or welding. External ground rods or earth connections get bonded together with heavy wire or conductive strap. Okay, so we're going to talk about strap in a second. A lightning arrestor, all your lightning arresters, which are different from grounding, they are in line with your cable. And if a high voltage occurs, what a lightning arrestor would do is, okay, so here's your cable coming down. It connects to here. Your shield connects to here. If there is a big voltage that forms, there is a gas-filled tube right in here, in between the two. Normally, that gas stays a non-conductive gas. But if there's a lightning strike, you may see, for instance, 30,000 volts on your center conductor. If it hits your antenna, what will happen is this will now be at 30,000 volts. The spark will jump across the gas, ionizing it, and then you now have this shell of your lightning arrestor at 30,000 volts. You tie all of your lightning arresters to one big metal plate, and then you ground that so that hopefully that lightning strike gets into the ground before it goes down the cable and gets into your equipment. What's the better thing to do if you know there's a thunderstorm coming?
Turn your radio off
And disconnect the cable.
and disconnect.
Disconnect the cable. I was actually once at a field day site. If you haven't done field day is basically an outdoor ham radio event that occurs in late June. And this was in Maryland, and we had a thunderstorm roll through, and we had a tent connected to a Yagi antenna. And we ended up having our equipment, and we knew it was coming through, and the sky opened up, and so we said, we better disconnect the cable. So essentially we took the radio out of the loop. Well, what we saw was, here's the cable coming in. This is a very good you asked a very good question there. So here's the cable coming in, and here's the connector. Here's the barrel of the connector, and here's the center pin. And we kept hearing, and that was little arcs between the center conductor and the shield. It takes a lot of voltage to do that, doesn't it? I mean, that
definitely fry a radio.
Yeah, that would fry a radio for sure. We could actually see the arcing that was basically static that was being collected by by our antenna, and it was arcing, just little static sparks coming down the cable. Yeah,
but that was a mobile. It wasn't properly grounded, correct?
Oh, that was an ungrounded system. It was out in the field.
Would it be wise to create some sort of a ground plate with connectors to terminate your feed lines when you disconnect them from the radio?
Not a bad idea. Yeah. I mean, it's not
you
as critical. I mean, the center conductor of your cable, if you get a direct lightning strike, it's gonna be a fuse.
No, yeah, it's gonna melt. Yeah.
It's gonna become a fuse. So all you can really hope for at that point is that you protect your equipment.
Yeah.
Scott, I'm in Tampa, Florida, which is considered the lightning capital of the world for strikes. And you say disconnect the end from your radio. Mm-hmm. People say, "Oh, put it in a glass jar, put it out in the ground."
Yeah, that's fine. Keep it dry.
Yeah. keep it dry. Don't obviously keep it in the house or near anything else that it could jump.
Right, because it will arc. And there's two different things. There's an actual lightning strike, and there's just general static buildup. Both are not good. A lightning strike will, actively fry something if it's connected.
We have what we call blind lightning. There won't be a cloud in the sky. There won't be anything. And 7-8 miles away, I was sitting next to a tree about 4 feet away that got struck by lightning with no indication that it was coming.
And you can
that
still
was
hear.
Interesting.
Yeah. And you can still hear, which is good.
Oh, yeah. Yeah. It's a miracle.
Okay. So now we're going to cover grounding. And this is something that isn't really necessarily covered in the book. What is ground, everyone? What is ground?
The earth.
It's the connection to the other end of the circuit, right?
Ground is defined as our 0 volt connection. That could be ground in a circuit. It's just 0 volts. Now, colloquially, ground is the earth. And when we think about, let's say, grounding a house for safety, right? We're going to use green wire because green wire is ground, and we go like this, and we have another one that comes up here, and another one, and we connect all of our grounds together, and here's another one, all of our outlets. Ground exists everywhere, right? It's great because if there's a ground fault device, it will sense that there's current flowing to ground. They're uneven. It'll turn off your device and protect you. So this is safety ground. So it could be that your ground wire from your outlet to your ground point down here, that could be, let's say, 200 feet long. What is the wavelength of 60 hertz? 60 hertz is our commercial power grid. 60 hertz has a wavelength of 5,000 kilometers. Okay, what is 5,000 kilometers?
3,000 miles.
That's New York to LA. That is the wavelength of that. So let's say that I considered this piece of wire to be an antenna. What is 200 feet compared to 5,000 kilometers? Insignificant. Agreed? Does everybody agree with it that it's completely insignificant? Okay. But now let us instead look at the fact that we are using, let's say let's go with something that even gives us a chance, the 40-meter band. For this case, we can approximate 40 meters as about 130 feet. Well, okay, now what do we have? How long was that wire in our house that's connected to ground?
200.
200 feet. So we're going to connect a radio right there. And we are going to look at how far it is from the radio to our earth ground. How far is it again?
200 feet.
200 feet. What is the only requirement looking at this? What is our only reference point? We only have one reference point, and ground is at what voltage? If ground is at 0 volts, what happens? Considering that every wire is an antenna, we know that ground is at 0 volts. We can start drawing waves on our antenna. And how long is our wave?
130 feet.
130 feet. Well, if we're at 0 volts here and we now are at some other point, we can start drawing voltages. And at some point, we'll go back down through 0. At some point, then we have our wave here. And then it flips and it goes like this. And what is our voltage at our equipment? In order to meet the one boundary condition, which is that ground is at 0, what is our voltage right here?
Should be 0.
It's not 0, is it?
No.
No, because there are waves, because that wire is an antenna. That wire is an antenna. Every piece of wire is an antenna. So now the case of my radio is perfectly safe at DC because it's grounded. It's perfectly safe at 60 hertz. How about at 7 megahertz, which is 40 meters? I have a significant voltage on the case of that radio. And it's an RF voltage. So somebody asked what happened when I was leaning forward on my second-story house where I lived with my parents and leaning forward and transmitting at 100 watts. My system was grounded and I was talking into my microphone and I got a little too close. Where did I get an RF burn and from what?
You got it on your lip, but it was from the radio frequency heading back to ground.
That's right. I got an RF burn on my lip by leaning too close to the metal shield on the microphone, which was at the same voltage as the radio case. But it was far enough away from the RF. It was far enough away from ground that it was not at RF ground. It was at the case. The whole case was floating around at an RF voltage. So what does that mean for grounding? If you're looking at RF ground,
keep the line short.
Yeah, if you can, even if your house is grounded, let's say that this is your desk and here's a piece of equipment and here's your ground rod. That's it. You go to an outside ground rod and put in a new one as fast as you can, as close as you can. and keep that ground cable as short as you can. The other thing is that if I were to draw a piece of wire, go ahead.
Would you also need to, yeah, I understand the ground closest to your equipment, but would you also need to bond that with your other ground?
Um, yeah,
Or
I
is it
would.
far enough away
It
maybe
it
that it doesn't have
it
to
might
be?
not matter. I mean, there's actually a very good book called Grounding and Bonding for Amateur Radio. It's a fairly short book, but it's a really good book. Okay, so here's a piece of copper wire. If I am Now I'm going to take I want to do it this way. Here's a piece of copper wire. If I am sending DC current through it, the DC current uses the entire cross section of the wire. As I run AC through it, I get something called the skin effect. The skin effect means that the amount of current that flows toward the outside of the wire is higher than at the center, and it changes with frequency. So at AC, I might have a lot of current flowing near the outside and some toward the inside and just a little bit toward the middle. When I get up to RF frequencies, virtually all of the current is flowing right on the outside. So that being said, which conductor shape takes better advantage of surface area? Which conductor shape takes better advantage of surface area? Something
Flat.
round or something flat?
Something flat.
Something flat. And that is why most of the time when we do grounding and bonding, instead of wire, which is round, we take our copper and we mash it into a flat strap. Because that maximizes the surface area. That makes a better ground cable.
Interesting. Okay.
Okay. Let's see. We're going to unshare here. And we're going to go back to over here. And one thing we're going to mention now is, okay, RF hazards and radiation exposure. Everything you need to know can really be found by looking at some RF calculators. Remember at the very beginning of this, remember we talked about ionizing. We talked about ionizing and non-ionizing radiation. Radio frequency is non-ionizing because the photons and the waves don't have enough energy to cause cellular damage. Oh, X-rays, radioactivity, gamma rays, beta particles, those can actually get in and destroy DNA.
Won't they
That is
still heat
ionizing
you
radiation.
though?
Oh yeah. I mean, think of a microwave. A microwave uses RF, but it won't damage the DNA in your cells. That's the difference between ionizing and non-ionizing. However, because it can still cause heating, we do have to do RF exposure calculations. No matter what your station is, you need to go through and do an RF exposure calculation. There are 3 ways to do it. The station licensee is responsible for doing it. You can follow the FCC OET Bulletin 65, which is quite complicated. You can do computer modeling, or you can actually walk around with a field strength meter and nobody does that, but you're allowed to. The easiest way to do it is the fact that the ARRL and several other people out there have essentially taken computer programs and used them to duplicate what FCC Bulletin OET 65 is. And for instance, if I go to, I'm going to stop sharing and I'm going to start sharing this. HintLink RF power calculator. Okay. This is one of several. Notice ARRL has one as well. This implements that bulletin 65. So I can say, okay, I have 100 watts and oh, look, antenna gain measured in decibels compared to I. That's an isotropic radiator. It's important to note that dB compared to I, isotropic radiator is a theoretical antenna that transmits in all directions at the same strength. Doesn't exist in nature. So a dipole is 2 dBi. So we're going to say it's a dipole, but now let's say it's a little better than a dipole, 6 dB. We are 10 meters from the antenna, and we have to select a frequency of operation. The reason we do this is because the human body behaves differently at different frequencies when exposed to RF. It typically gets worse at 10 meters and 6 meters. So just for the heck of it, we're going to choose a 10-meter band and go. Okay, so we have our controlled environment, which is I am controlling the area. I have it inside a fence. I have it in my attic. Everyone in the area, the general public is kept out of it. Everyone in the area knows what's happening because I've told them. My limit is 1.15 milliwatts per square centimeter, and I'm way below that limit, even at a distance of 30 feet. Uncontrolled, notice that I have 1/5 as much available power. I'm still below that, but that's basically protecting the public. So when we have a station at Eugene Science Center, which we do here in Eugene, one of the things that we have to do is we have to do an RF exposure calculation because some people know that we have a transmitter there and some people don't. We have to assume that nobody does. So we look at the distance, we look at the average power levels, we look at the fact that it's a dipole, we run the numbers, and we come up with a safety rating, and we find that it's safe at up to 125 watts. And since our transmitter doesn't go anywhere near that, we don't have to worry about it. But we did have to run it. If you put in a station, this is one of the requirements of having a station. Averaging time, duty cycle determines what the average duty cycle is, the average amount of time that your transmitter is transmitting. So if you're 10% on and 90% off, you have a 10% duty cycle. If you transmit at 100 watts 10% of the time, that's essentially an average of 10 watts of exposure. So one of the things about doing that is it affects the average exposure to radiation. And if you change your duty cycle from 100% to 50%, your factor goes up by a factor of 2. You go from 100% to 10%, your peak power goes up by a factor of 10. And again, the human body absorbs more RF energy at certain frequencies than others, and the peak occurs at 50 megahertz. Near an antenna, what factors affect the RF exposure of people near an antenna? So if you're if you have an antenna that is a dipole and it has if it has that donut shape pattern around it, that's not particularly strong in any one direction, then the exposure is much less than if you took a microwave dish and pointed it directly at somebody's head. They're completely different things. So let's say that you have a very weak 1 watt transmitter, right? You just have a very simple 1 watt transmitter. And what we're going to do is figure out if a very simple 1 watt transmitter can cause anybody any harm. So here's a 1 watt transmitter right here. And we have this connected to a microwave dish, which is a repurposed dish that somebody threw out into the trash. So you managed to find it and it was free, and here's your feed point. And because it's a parabolic dish, all the energy goes out in this direction. And this has a gain of 30 decibels. You found a big dish. What is 30 decibels? Remember, we covered this yesterday. 30 decibels is 10 dB plus 10 dB plus 10 dB. And every time you have 10 dB, how many times do you go up in power?
10.
10 times. What's 10 times 10 times 10?
1,000.
1,000 times. So I have a weak little 1 watt transmitter. How much effective power do I have going in this direction?
1,000 watts.
1,000 watts, right? I only have a 1 watt transmitter, but I've made really good use of it. This can really cause some damage to somebody, even just with a little 1 watt transmitter, which is why it's important to go through these kinds of calculations. Okay, moving on. And we're getting to a good break point for Kent. Um, how can you make sure that people are not exposed to RF radiation? You can move your antennas. You can also transmit less. So, how can you make sure your equipment stays in compliance with RF safety regs? If you change your equipment, if you change your antennas, if you change your feed line even, because feed line might be less lossy, you can no longer take that loss into account and you have to go through and recalculate. So now we're moving into station setup and operating controls. And this is basically building a station. And with that, Kent, take it away.
Hi, good morning. Good morning, everyone. Now you got a crowd on here, Scott, right?
Yep.
Good. Well, thanks for letting me in. I'm Kent Petty. I'm KL5T is my call sign. And right now I'm in Nikiski, Alaska. It's pretty cold here this morning. But anyway, congratulations to everyone who's working on their license exam here, getting ready. Scott will give you excellent advice to help you pass the exam. I'm here because we are putting on a special testing session for this class tomorrow. We've got 35 examination slots. Currently, it's completely full. Oftentimes we do have people drop out at the last minute. We've had a few people drop out, so they're popping in and out as far as that goes. I would like to get a sense if there are additional people that do want to take the exam right away to get that word out to us. I'm going to drop a note in the chat here momentarily that will give you a little bit of information, including the link to register for one of our other exam sessions. We do test twice daily, every day, Monday through Saturday. Okay, so there are plenty of opportunities to get in and take an exam in the next few days or week or whatever you'd like. So with that said, Scott, do you have any questions for me? Do you know folks have anything specific they need to query me about?
Well, the most important thing is that if there's anyone who needs to go like first during the exam session, we'd like to know that so we can put you on first, get you done early. If you need to go toward the end, I think we start at what, 10 o'clock Pacific?
Yeah,
tomorrow?
10 Pacific. Yeah, 10 Pacific.
And it's going to take a while. I mean, we test one person at a time with 3 examiners or 4 examiners. So it can take a while. So this whole process is probably 4 hours. So if you are, it's not like everybody's in one big Zoom room at one time. So if you're on the East Coast, we find that some people on the East Coast, if they have family things going on, if they have a softball game to go to, not this time of year probably, but basketball game to go to, then we'll do our best to accommodate all that. JD usually has me running the phones. If you don't have your cell phone number updated, you really need to. And if you see a number come up that doesn't look like something you recognize, please answer it, because that's how we're going to get a hold of you.
Yeah, Scott, and just to clarify, when he says that we test one person at a time, that's in each room. We'll have multiple rooms running. Well, hopefully we'll have 5 or 6 exam rooms running, or maybe even more, depending on how many VEs we can pull together. And And I see a lot of questions coming in about how do we arrange our exam slot. I'm going to drop the link in, or as far as tomorrow goes, we just ask you to wait for our call before you join the Zoom session. Okay. We're going to work through them. And like Scott had mentioned, if you've got a special request, if you really need to go early or you'd like to go late, let us know so we can make notes about that. Okay.
There is no time limit.
No time limit. That's right. And just be sure, make sure, remember, we've got a 2-camera requirement. Most folks just use their cellular phone as their second device. And don't worry, when you come in, that's the first thing we're going to do is we're going to help you get set up. It's a piece of cake. We do this all the time. But the notion is on your second device, you just join the same Zoom session. The key is don't turn the audio on your second device, because then we get all kinds of feedback. So just join with your first device. We'll get that set up. Then we'll say, okay, bring your second device in. Okay. So just kind of don't get ahead of yourselves on it. Let us guide you through this. We're pretty good at it. All right.
The other thing is if you have signed up for an exam and you want to reschedule it, do it as soon as you can so we know that there's a new slot that's opened up, because there were 3 or 4 people who said that they wanted to take an exam but hadn't had one available yet and hadn't signed up. The other thing is that if you can honestly, you can take an exam with anybody you want. You can take an exam with any volunteer examiner coordinator's exam session. It does not have to be this group. It could be, any number of them, not to, say anything about the Anchorage group, because Kent is great. He does a fabulous job with it. JD is great, does a fabulous job. I think JD was here too. So, but if you find something that, meets your schedule and you want to take it, there are lots and lots of exam sessions. We did this one just basically for your convenience so that you didn't have to necessarily fight for it, to get a spot.
And just be sure, remember your testing environment, imagine that you're the examiner and you're looking at someone remotely. We obviously don't want to see a bunch of materials up there that would help you with the exam. We need you to make your environment as sterile as reasonable. So clear your desk, get anything related to this activity away, no documents, charts, whatnot related to amateur radio or basic electronics. Okay.
Yeah. And the other thing is if somebody busts into your room, we have to start it again. So wherever you're taking it, it has to be sterile in that regard. And we've had people go in the bathroom and put a sign on it and lock the door and says, "I'm taking a test. Don't bother me." That works really well, actually. So Jason Gibson, did you see that? Jason Gibson would like to schedule for a later date.
Okay, I see that. So Jason, and for everybody, I'm gonna put 2 posts up. The one post is gonna be a link to, if you haven't registered, that shows you all of our other sessions that are available. And I'm also going to put a separate post up here for how to start the rescheduling process. Okay. So that'll be up there. As soon as I get off, I'm going to dump it on here.
Okay. And Alex, how does the general exam work? Alex, do you plan to take the general tomorrow as well? Do you plan to take them at the same time? Because you can. If you crush the technician exam and you've prepared for the general license, then you could take them at the same time.
We just ask you if you're going to attempt the exam, that you're actually ready for the exam.
Yeah.
Hopefully many of you have been taking practice exams. I hope that you have. I think it would have been really interesting for all of you to have taken a practice exam or 2 or 3 before you started Scott's class, and then now take exams after the Scott's class to see how you're doing. That'll give you a great indication if you're ready to test. 74% is a minimum passing score. So that's 26 questions right out of the 35. Okay. And don't worry, I see a question about how do you let the examiners know you want to take both. You just come into the session, and if you're ready, if you say to us, "Yes, I'm ready to take the exam," we're going to let you take the general as well. Or if you're ready to take all 3, if you want to go zero the hero and you think you're ready,
happens.
We do it. but a lot of material. But we're
Yeah.
happy to test you. Okay. All right.
So everybody, just remember our goal is to get everybody here eventually pass with a license. It doesn't have to be tomorrow. It doesn't have to be next week. But you know, you're going through the effort of spending all this time and studying and all that other stuff. So our goal is to get to there.
And Jude, how old are you?
I'm 15 and I'm going to be taking the test tomorrow. So
outstanding. You know, we hear a lot of stuff about, you know, we're not getting kids into amateur radio. And, you know, as chairman of the VEC, I see kids taking exams all the time. So Jude, this is going to be a great thing for you. You will cherish this for the rest of your life.
Yeah, I'm scared I'm not going to pass, but I've been taking practice tests and I've been getting above like 80%.
Oh, you're ready to go. You're ready to go. Okay.
And by the way, he goes to South Eugene High School, it turns out, and we didn't even know each other. We didn't know that till today, and we're getting ready to use that $17,000 bucket of money that we got.
Outstanding.
Are you guys also part of the Oregon Valley Radio Club or
Valley Radio? Yeah, I'm the trustee of the Valley Club.
Okay, awesome. I'm probably going to be going to one of those meetings. So.
I'm going to miss the next one. I'm going to be in Louisiana.
Yeah, cool.
But January. Yeah.
So Scott, just last thing I'd like to say to the group is, listen, when you're taking this exam, I know taking exams could be a very nervous thing. People can get really nervous about that sort of thing. Just please do your best to recognize that a couple things. Number one, we want you to pass this exam. We're administering it to you. We want you to pass. You need to feel like you're in a room with friends, okay? Because that's really what we want. Okay.
So as far as minors, as far as who has to be there to start the exam, notice there's also a comment from Leighton, who I believe is also 15.
I see that.
14.
14. They have to be signed in by an adult, and what ID needs to be present?
Yeah, I see. Well, it would be great if you had some sort of ID. Yeah, a permit will work. Absolutely. We want to see a government issued photo ID is what we like to see. But if we've got a parent there as well, then that's very helpful. And don't worry.
Passports? Yeah, passports.
Absolutely. Okay. Yes, absolutely. Any government issued photo ID will work. Okay.
Now, does it have to be U.S. government?
It does not. It has to be any U.S. government photo ID will work, including U.S. passports. We will accept foreign issued passports so long as they're written in English. There's only 2 countries that don't issue them in English, and we're not going to have that. So
okay. Joe, do you want to ask Kent any questions offline?
Well, yeah, I'd like to know if I can apply for the exam, but I do have my passport, but I don't have any U.S. address. I mean, there's no mail address. So if that's possible for me, I'm from Italy, from Europe.
Yeah, well, those are 2 separate things. Yeah. So the address, you have to have you have to have an address in the United States. The reason for that's not our stipulation. That's the FCC. We don't even have the ability to put a foreign address into the system. They will not accept it. I'm sorry. So,
okay.
A lot of people, maybe they've got friends or family, or they actually use a mail forwarding service in the States or something like that. I would caution you to making up an address or selecting someone else's address to use. We see that often, and that would be mail fraud. You don't want to get tangled up into that. Okay?
Yeah, okay. I understand that. What about the ID? The ID shouldn't be a problem.
Yeah, passport.
Yeah.
Okay. No problem.
Okay, perfect. So I will work something out. Thank you very much.
Okay.
Cheers.
Great.
Okay. Any other questions? And yes, you could get a PO box.
Yeah.
I have a question.
Yep.
How long will it take to get your call sign once you pass the exam?
Good question. Okay. So we file with the FCC as soon as possible. If you're testing on the weekend, we find that submitting on the weekend is a bad thing. The FCC systems are kind of antiquated. So we'll wait till Monday morning, or as soon as they're open for business on Monday morning, we'll make the batch file submission. By the top of the following hour, they'll pull that file that's in the processing queue. They'll do a quick 1-2 minute automatic process on it. And you will then receive an email from the FCC saying, hey, got your application. Now go pay us your $35 fee. Do not pay, even though they say it will now, don't try to use your cell phone or device. Use a regular computer to do that, because their website doesn't play well with devices
so wait
like
till
this.
that email to pay for the link, or to
What's
pay.
that?
Wait for the email and then pay with that email link.
Yeah, you won't be able to pay until they've got it.
Awesome.
Okay. And don't worry, even if something goes awry, if you don't receive the email, we keep an eye on every one of these applications, and we carry them through all the way to the end. So we're watching you until we see that your call sign has been issued. So, but if you receive the email, don't wait to pay. You got 10 business days to pay. Don't wait. Get right in there and pay it right away. Okay?
Awesome. Okay. Thank you.
I have a question. I'm taking the exam, but through a different group. Is it going to be basically the same process?
Every group every group has their own process, but they're all going to be the basics are all the same. Like, for example, we use 2 cameras, and we do, there's just going to be little things that might be different between each group. Okay. But pretty much all the same.
All right, great. Thanks.
Does a does a photo of a passport work on the phone? Kent?
Yes. We just need to be able to, picture needs to look like the person. That's the big thing.
Okay. How do we access the videos to watch later?
I sent out, did you get the link for the first one last night? An email?
I got an email.
I sent it out to everybody. So if it's at YouTube unlisted video. Okay.
Gotcha. Thanks.
How long after you do make your payment would you expect to get your call sign?
Good question. After you pay, typically within about 24 hours, your call sign will be issued by the FCC.
And we were going to cover this.
Pretty fast.
I had to wait a month.
So for example, if you test tomorrow, we'll submit first thing tomorrow morning. If you pay right away, there's a chance your call sign could be issued Monday night. If you test tomorrow, we'll be filing Monday morning. If you pay right away, there's a chance you might receive your call sign by Monday evening, but likely it will be Tuesday.
Yeah.
I know we don't have control of the FCC. We try to we hold the torch near their buttocks and try to,
it only works
in a week.
It only works so well.
Yeah.
Yeah.
No, we do pretty good. As long as your system, every now and then they've got system problems, and then we're like, oh geez. But don't worry, it's not going to get lost in the ether. Okay. Don't worry.
Hey, Kent, what year did you get licensed?
1989.
Okay. I was 84. And how long have you been a VE?
Oh, I've been a VE since the mid 90s.
Okay. I was a W5YI starting in January of 87.
Very good. Well,
we've both been VEs for a long time.
Yeah. And just FYI, the Anchorage ARC VEC was the first VEC in the country in 1984. And we issued the very first exams on behalf of the FCC as a VEC. Pretty cool.
Hey, how do I remove myself from the exam tomorrow?
I'm gonna post a link up here. I'm in the chat. I'll have the link to start the rescheduling or cancellation process.
Alex,
that's the best way.
And Alex, we're going to talk about that.
Okay.
Okay. Thanks.
Yeah, as soon as I get off here, I just got too many things going on. As soon as I get off, I'll make the post. Okay.
All right. Anything else? Anyone else?
I live in the local Eugene Springfield area, and I was wondering how many ham radio clubs are there in
We've
the
got
area.
we've got two local ones and one statewide DX club, and then all the way up and down the valley and over to Bend. And yeah, we have 50 roughly 50 clubs in the state.
All right, thanks.
It's a lot. The Valley Club is 160 plus members. That's the one I'm the trustee of. All right, Kent, thanks, man.
All right. Good luck, everybody. And congratulations. And I wish you all well. And happy holidays.
All right.
And the posts are coming on chat. See you later. Thank you, Scott.
Yep. Thank you, Kent.
Appreciate it.
All right. How about a 5-minute break for everyone?
Thank you.
Sounds good.
Okay.
Yeah.
Thank you.
Sorry about that, everybody. I forgot to I dumped off the Zoom before I made the post.
Hey, Kent, would you be able to answer a question about vanity call signs?
Absolutely. Just give me 1 second. Let me get this guy on
Giving
here.
you some time.
I'm doing my best here. Let's see. I'm almost here we go. This is what I want. Okay. Hi, Sherry. Yeah, go ahead.
Hi. Okay, so I noticed there's like the different formats, one by one, there's different ones. If you can search by call sign to see if it's already taken, and then if it's not taken, then there's an additional fee to request it.
Yes,
Okay.
there is. Yeah.
So then I'm guessing I will learn if the 1x2 or the 2x3 or whatever, which one is applicable for where I live.
It's a function. Well, yeah, there's
a function of your license class.
Yeah, license class, and then if you live in Alaska, there's a lot more available to you than if you live wherever, because as far as structure goes. But yeah.
Okay. All right. No, I was trying to match it to my tail number. So
excellent.
Similar. Yeah.
Yeah.
We'll see.
Yeah. What's your tail? Oh, yeah. Oh, so, yeah. Well, you'll figure it out.
Yeah.
So if you go for your tail number, it'll I mean,
what's your tail number?
It's November 9052 Delta.
I'm not sure how you do
It'd be a
that.
K. It'd have to put a kilo in front of it, right?
Oh, Kilo
Well,
Charlie.
you can only
9
have
Delta.
one number.
Yeah.
You can only have one number.
Okay.
Yeah, one number.
So you
I'd
could
have to choose one.
But you know, I know in aviation comms, you'll truncate once you've established comms, you'll truncate your call. And so
Yeah,
what
I
is your
do.
call sign?
It's Niner. I shorten it to 52 Delta. I'm a Stinson, so I usually say Stinson
Oh,
52
I
Delta.
see. Yeah, 52 Delta. Okay.
Yeah,
That's a
you
tough
can say.
one.
I mean, mine's pretty short because it's a super old plane, so it's Niner 52 Delta, but I don't really say the whole thing, so I usually shorten it.
You'll figure out something clever.
Yeah.
Maybe somehow work Stinson. Is there an abbreviation for Stinson?
It's just an S.
STN, yeah.
Yeah.
I don't know.
Yeah, it's just a Stinson. It's a 108, so it's most people don't know what a Stinson is. So when I say Stinson, they're like, "What are we even looking for?"
Well, I don't fly real aircraft, but I used to fly remote control aircraft, and guys had anyway.
Yeah,
fun times.
It's
good for
actually,
you.
It's a great Alaskan bush plane. I have a friend up there that flies one just like it. So
Very
all right,
cool.
well,
all right. Are we ready?
Good luck.
We're ready to get back and plow through the rest of this. We still have a lot of material to cover. I know that sounds great, doesn't it?
Sorry, Scott, very quick question, if I can.
Yep.
Okay, pretend that I can find a friend who can help me out for the grants in the US. What should I tell him to expect in terms of a post or ordinary post that will come from who? The FCC maybe? Or someone else?
Honestly, I would say you will virtually never get anything through the mail from the FCC, but you have to have an address.
Right.
I don't
so
think
nothing. Okay. Sorry.
So it's really up to you. Like I was talking it over. I work a lot in Canada. We have a company address, and I checked it out with a friend of mine who's an examiner in Canada. He said, "Yep, that'll work." So I took my Canadian license exams.
Right. Okay. Cheers. Thank you.
Okay, let's go. Here we go. Station operating and controls. Okay, this is where we start to get into the meat that runs your equipment. So first thing you have is a power supply, because most equipment runs at 12 volts DC or nominally 13.8. They call it 12 volts DC. And the reason that is true is because transistors operate at DC, oscillators run at DC, everything runs at DC. So it's easier to just provide a system that runs off of 12 volts DC. So why do you use short heavy gauge wires? Because wires have resistance. Resistance causes voltage drop. You might have, if your cables are long enough, you might have a 13.8 volt battery. By the time you get to your radio, you only have 10.5 volts. When you key the radio, your voltage drops even lower because your voltage, VE equals I times R by Ohm's law. And now you only have 9.5 volts and your radio turns off. So you want short, fat wires. Typically, you also want to go straight to the battery if you're in a car. Okay, typical 50-watt output transmitter. Okay, did somebody tell me what Ohm's law for power is? P is equal to what?
I times
volts
E.
times
Okay, volts times
I squared R.
or I squared R. Yeah, okay. P is equal to I times E. So if we look at a 50-watt radio that runs at 13.8 volts, that would say that we need about 4 amps, right? But the answer to that is wrong. The reason that that's wrong is because your typical RF transmitter that's in a radio is only going to be about 50% efficient. So if it's a 50-watt transmitter, that means that it's going to be putting out 50 watts of radio frequency energy. It'll also be dissipating about 50 watts of heat. which means that you need 100 watts plus a little bit to make sure that, you can run the lights and you can run the CPU that's running it. And you have the audio circuits turned on. And so by the time you're all done, you're really looking at a 12 amp power supply. If you run a smaller power supply, what'll happen is the power supply will shut down or your radio will turn off because the voltage dropped too much. And that is because of efficiency. Okay, computer to radio interface for digital mode operation. Okay, so now we're going to talk about how to connect a radio to a computer, which is something that a lot of people do. Okay, everyone see the whiteboard, I hope? Okay, so we have our computer and we have our radio. We'll call it a transceiver. That's a TRX. Transceiver, transmitter, and receiver put together. So we have 3 wires that connect between the two things. We have the speaker output of the radio goes to the microphone input of the computer. The speaker output of the computer goes to the microphone of the radio. And then we have this thing called push to talk. Push to talk is something that is generated in the computer that causes the radio to go from receive to transmit. That's it. That's our interface. There might be other wires that we use, but fundamentally that's what it really is. The audio out goes to the audio in of the other device, and the audio in goes to the audio out of the other device, and then push to talk. Okay, other things with regard to that, and if anyone is curious, we are on page 74. So, line in on a computer is the same as microphone. Line out is the same as a speaker. So we now also have this thing called we have shielding. Okay, so let's say we have an audio cable which has 2 wires in it. Every piece of wire can function as what?
An antenna.
An antenna. That means it can transmit energy and also receive energy. So what happens if there's a microphone here and the radio over here? Here's your microphone connected to the radio. You have this piece of wire. What happens if there's RF floating around in the environment? What is the microphone cable going to do?
Pick it up.
It's going to pick it up. And since you're transmitting, here's your antenna, there is going to be RF floating around. If you get that, you will sound all distorted and weird. In order to prevent this from happening, there are a couple things we can do. We can take the shield of the microphone cable, and we can ground it to the radio. The other thing we can do is that we can take the cable, and if it does happen to catch some of that RF energy and try to conduct it back into the radio, we can take the cable to this point. We can put something called a ferrite on it, or a couple of ferrites. A ferrite is a piece of magnetic, I guess it's a ferromagnetic material, usually shaped in the form of like a donut. It could also be a ferrite bead, which can be a clamp on. And essentially what this thing is a piece of material that looks like that has a hole in it, and you run cable through it. Okay, so if you have a current flowing right here, what does a current generate, everyone, as it's flowing? What kind of field? A magnetic field. Generates a magnetic field. Well, this ferrite is usually made of nickel, iron, manganese, other metals in a powdered form that tend to provide a really nice path for magnetic fields. But the choice of those metals is such that once they get in there, they just sort of spin around until they die. Well, if you've used up the energy, as heat in there, how much is still there on the other side?
Theoretically, none.
Theoretically, nothing. This is called a choke. That's an RF choke. And the core of an RF choke is a ferrite from iron. That's what ferrous materials are. That's a ferrite choke. The other way to do this is you can take this cable, and here's your ferrite again. And depending on how it's built, you can go like this, wrap it once, wrap it twice, wrap it 3 times, 4 times, 5 times, a whole bunch of times, and then it comes out the other side. Every time you wrap it, it works like exponentially better. So if you have a thin cable or a big ferrite core, then wrapping it a bunch of times does a lot of suppression. You may actually have some of these laying around and didn't even know it. I've got one right here, and it looks like this. Hold on, let me grab my pencil. Okay, can everybody see me? Anyone see this?
Yes.
This is on my power cord. And why is it there? Why is it
To
physically
reduce
there?
interference.
Yeah, because computers run on what power? AC or DC?
AC.
DC
They run on
internally.
DC. Yeah, that power supply generates DC. AC in the form of radio frequency energy is not good for electronics. So by putting this thing on the power cord, that basically chokes out any RF that might be getting into the computer, which is why it's usually very close to the computer and power entrance as well. Okay. Next thing. Okay, so that's RF chokes. Which of the following conductors is preferred for bonding at RF? Oh, there's our answer. See that flat copper strap again? Why is flat copper strap better than just plain old wire?
Larger surface area.
More surface area. Good.
Skinny
Okay.
effect.
So where should the negative power return of a mobile transceiver be connected in a car? You go right back to the battery. And the reason that is because if you think of the way a car is built, you have, let's say, a light. You run 12 volts out to the light, you turn it on and off, and the light is then connected, the negative side of the light is connected to the frame of the car. Well, that's great for the frame of the car, right? Everything is, in theory, bonded together. The question is the frame of your car suitable? Is it designed to handle a return current of 25 amps? I don't know. Is it?
You have to ask an automotive engineer.
Yeah, I don't know.
I doubt it.
So the easy way to figure that out is to say, I'm not even going to ask the question. I'm just going to run my own fat cable. So you just run your own fat cable back to the battery.
Straight to the source.
Yep, right to the source. Okay, looking at batteries, something called watt hours, a watt hour rating or an ampere hour rating. Sometimes these are used interchangeably. An ampere hour is the ability to store 1 amp's worth of current and be able to dissipate that for a certain amount of time. So a 10 ampere hour battery can deliver 1 amp of current for 10 hours. That's a 10 ampere hour battery. In theory, a 10 ampere hour battery can also deliver 10 amps for 1 hour. That's not necessarily true, but that's how the calculation comes into play. Sometimes you'll see batteries calculated in watt hours. And since a watt is a volt times an amp, if you have a 12-volt battery that stores 10 amperes, 10 amp hours at 12 volts again, that could be listed as a 120 watt hour battery. But usually we just assume that everything's 12 volts, so we use amp hours instead. Operating controls. Okay, the effect of excessive microphone gain. So I know, Joe, your voice was actually a little bit distorted. I think that the pickup on your computer is a little bit hot. You have a little too much mic gain. Did anyone else notice that?
I was going to say that's a good demonstration of overmodulation.
Right. And that's and that's what happens when you drive an amplifier too hard. It basically overdrives the signal and it drives it into saturation where it's no longer linear. So Joe, when you if you can back your mic gain down, you want to try again?
Maybe the sound of the external speaker is not the laptop itself, but it's going into a hi-fi system. Maybe that. Not sure.
Okay. Well, on your computer, if it's in the computer, you should be able to adjust the microphone gain in Zoom even. So, but anyway, if you overdrive something, that's what happens. Similarly, if you underdrive something, it'll sound too quiet. So,
is it any better?
Oh, that's much better.
All right. So
that's way better.
Perfect. Yes. That was a great example. Okay. What's the result of what's the result of tuning an FM receiver above or below a signal's frequency? It'll sound distorted because as the frequency swings back and forth, it won't have a center frequency in the right spot. Which of the following can be used to enter a transceiver's operating frequency? I've got my handheld radio. It's got a control knob up top. It's also got a keypad. I can enter it directly on the keypad. Most radios today will have that. The knob is known as a VFO knob, which is a variable frequency oscillator. It used to be that the VFO knob would actually control an air variable capacitor, and the air variable capacitor would change the amount of capacitance, which would change the operating frequency by changing the resonance. To access a favorite frequency, you store it in a memory channel. The scanning function of an FM transceiver that allows you to listen to many. I do it. I have 1,000 memories stored on this to scan through all those memories very, very quickly. Squelch. Squelch allows you to mute a receiver's audio when there's no signal. And what do you do so that a weak signal can be heard, FM or otherwise? You turn the squelch completely off. I can demonstrate this by going to, hopefully, if I still have it open, which I think I did. And we'll go here. Notice I have it muted. Okay, there's nothing to hear. I turned on the squelch. Look what squelch did. I said there's nothing to hear. I'm going to mute the receiver because there's no point listening to all that static. Personally, if I'm listening for something weak, I want to hear all that static because I want to be able to pick out the weak signal in there. This is another example of choosing the proper bandwidth for a signal. Single sideband requires a filter. Does everybody see the little yellow box down here at the bottom? Right here that I'm moving up and down?
Yes.
Okay. That little yellow box is my filter. It has a low end, which is closest to the vertical line. And let me see if I can, I can make it bigger. And it also has an upper end. So this is the low end cutoff. And this is the higher end cutoff. And I'm going to scoot it over here because it looks like somebody's busy talking and turn it back on. And that's what it sounds like when I have it too far open.
And stand by 5 minutes. Stand by 5 minutes.
So that sounds like an appropriate bandwidth for that particular signal, which is single sideband. If I go and find another one, let's see what this one sounds like. Okay, so everybody notice the other sounds that are kind of squawky? This is what happens when two signals occupy the same space. And if I were to try to narrow this down, notice how much of it we can hear. What happens if I pick the wrong filter? What happens to the audio?
Goes away.
because part of the information that I want to listen to is now gone. So an appropriate filter bandwidth is very important. So if I'm listening to, for instance, single sideband, let's say this one right here. So notice that's about 3 kilohertz wide. You can get away. You can get away with about 2,500 hertz, 2 kilohertz, 2,000 hertz. You can still make it out. But if you narrow this down to the same kind of bandwidth that you'd listen to Morse code with, it's gone. And that's because the filter bandwidth is no longer appropriate. So for single sideband, 2,400 hertz is okay. For Morse code, 500 hertz. For other modes, you could get even narrower than that. What's nice is that you used to have to actually go out and buy optional filters, which were basically little crystal lattice filters. Those would cost about $150 a piece, and they would not be tunable. Today, it's all digital signal processing. The fact that we're able to look at these signals right now, this is actually a software-defined radio. This is on the web. And the fact that we can alter this filter bandwidth, this is all being done digitally. It's basically a digital representation of something that used to be done in an analog fashion. So pretty cool stuff. And this is called a waterfall display for those who missed that. And that web SDR, there are hundreds of web SDRs all around the world. That particular one's in Utah. That particular site has 5 or 6 different software-defined radios that anybody can listen to from anywhere. Want to listen to yourself transmitting? You can do that. I've done that. Okay, the purpose of a squelch we covered. If you want to hear a weak signal, you turn the squelch all the way off. Repeater offset. This is the difference between a repeater transmit and receive frequencies. So it's almost time to talk about how repeaters work. A hotspot. This is basically a bridge between digital voice and data systems and the internet. That's a digital hotspot. A talk group on a repeater. This is group A or group B, essentially allowing a digital repeater to carry multiple conversations at one time. And in areas where if all the people who are on one particular talk group just hear each other and not the other group. How do you program a digital talk group? You look up the group ID code. A DMR, again, that's digital mobile radio. Something called a code plug is basically all the programming that it would need in order to function. So access information for repeaters and talk groups. And because DMR has a lot of internet-based stuff, a lot of repeaters that are on the internet on DMR, some of these code plugs are actually programmed with, for instance, 200,000 different accesses, different frequencies, and different groups to choose from. They grow they've grown really fast. How do you listen to a particular group of stations? You enter the group's identification code. There's also something called a color code. Color code must match the repeater color code for access. This allows multiple different repeaters to use the same frequency in a given area.
Masturbator light off. Oops, I'm sorry.
Let's see, a D-Star. Okay, D-Star is a competitor technology like VHS and Beta. D-Star is another form of digital voice. This is something that was developed by ICOM and adopted by Kenwood. Yaesu has something called Fusion, which is another digital communications mode. You must program your call sign into a handheld radio or a mobile radio before using D-Star, because that is actually sent along with your voice. Okay, multiple receive bandwidths. We covered that. For single sideband, 2,400 hertz is an appropriate filter bandwidth. For Morse code, 500 hertz. Something called RIT or clarifier is used to change the receive frequency without changing the transmit frequency. You probably noticed that when I tuned something a little off frequency, it sounded like we were listening to Donald Duck speaking. So let's say that you and the other station are slightly off frequency from each other. If you change your receiver frequency so that they sound right, now you're going to sound weird on their end, and you'll keep going back and forth. So the clarifier, or RIT, which is receiver incremental tuning, allows you to change one without changing the other. PTT stands for push to talk. And now we're going to cover repeaters. Okay, this is a repeater. TX stands for transmitter, RX stands for receiver, and in between them, we have something called a controller. That repeater controller is essentially a computer. The receiver on a repeater, the RX, receives signals at a given frequency, and we're going to say that that is 146.12 megahertz. It also listens for a particular CTCSS in some cases, which is a low frequency audio tone, which kind of acts as a gateway to allow the signal to be received. There's also something called a DCS, which is digital code squelch. That is a little frequency hopping sequence that it looks for as a gate to get in. So we also have, as this signal comes in, this controller. The receiver sends information, everything it receives, to the controller. The controller looks at that set of information. We have a signal coming in on frequency. If it's on the wrong frequency, the receiver doesn't hear it. We have a CTCSS and or a DCS, or sometimes neither, or sometimes both. The controller says, if all the conditions are met, I am going to take that signal and I am going to forward it to the transmitter. The transmitter then, because that's what it does, sends a signal out into the world, but on a different frequency, and it may have a CTCSS on it. It may also have a DCS on it, which your radio will have to receive. So the point of this is that we have a receive antenna and we have a transmit antenna. The difference in frequency right here is called the offset. On the 2-meter band, it is 0.6 megahertz or 600 kilohertz. And it can be plus or minus depending on the frequency that you are using. So if I were trying to listen to a repeater, like in our case, the W7PXL repeater, I would be tuned to 146.72. As soon as I transmitted, my handheld radio, so that the signal would be heard properly, will automatically, if I programmed it right, change my transmit frequency to 146.12 so that the signal can get received by the repeater and retransmitted. This is how it allows us to effectively increase our range, because this repeater, for instance, is at 3,500 feet in the coast range here in Oregon. Because the 144 megahertz band is mostly line of sight, this means that we are actually able to access this repeater and act as though we are on top of a mountain 3,500 feet up, looking out over everything. So if somebody can see the top of that mountain, or if we can see all those other people, we can be in mutual communications range. So with a handheld radio, because I can actually access the repeater from here, I have a range of about 60 to 100 miles in every direction, just with a handheld radio, because of this repeater system. Now, one thing that's interesting about a repeater system is that I have sometimes just one antenna, and it's connected to a transmitter and a receiver like that, because antennas are expensive and hard to maintain, especially if they're 3,500 feet and you have to have a key to get in. You have to have a four-wheel drive to get up there. So something has to be done because these are only 600 kilohertz apart. In order to do this, I need a combination of capacitors and inductors so that these two frequencies on the transmitter and receiver do not wipe each other out, because it would be very easy for this transmitted frequency to feed back into the receiver, which would then go into the transmitter, and I'd end up with a cycle around and round and round, and my repeater would lock up. It would always be transmitting. So what we're going to show is right now, if I have, yes, you can do an RF circulator. You're not supposed to know that. That's advanced. Okay, so if I have something that looks like a capacitor, we said a capacitor passes, it looks like a short circuit for really high frequencies. And if I do this, that means that, and this passes low frequencies. So this would be a low pass filter. Here's my in and here's my out. So I only get the low frequencies. I could redraw this. Here's another version of it, but I'm going to reverse the components. Well, the capacitor would pass the high frequencies, and the low frequencies would go this way. This would be a high pass filter. If I put two of these in series, I can pick those components so that there's a little bit of overlap. So if I were to do that, my frequency chart would look like this. Here's a high pass filter, 0 to infinity. And here's a low pass filter. If I were to put one in front of the other, I would get the intersection of the two, and I'd get something that looked like this. That's known as a band pass filter. That allows only a certain range of frequencies to pass through. I can also do this such that I get a pass band that looks like this with a very deep notch cut in it. That's actually called a notch filter. It allows me to reject one frequency. And all these are built with capacitors and inductors. So in order to protect my repeater transmitter from its, or to protect its receiver from its transmitter, I have to do something. I have to build a filter to do that. The filter would look like this. Here we go. This is why most individuals don't put up repeaters. This is why repeaters are most often put up by clubs. Can everybody get a, let me unshare my, oh, come on, don't fight about this. There we go. Okay. Can everybody see that? Those are about 3 feet high. And notice they have lots of very expensive looking fittings and cables and things like that. This is a band pass band reject filter that is, notice, 144 to 174 megahertz. This is designed to have an input and an output where the transmitter and receiver can both be hooked up, even though they're very, very close in frequency. And the way you do that, you see those little screws up top? Those are actually connected to plungers. And by changing the length of the cavity inside each of those are able to basically tune those cavity filters, as they're called. And notice how much one set of them costs for a brand new set. That's why most individuals don't put up repeater systems. That's why they're done by clubs, because they're very expensive. So the next time you use a repeater, realize that there is tens of thousands of dollars worth of stuff that you're using that you didn't have to buy. And that's why it's okay to support a club that that actually maintains a repeater, because it's an expensive thing. It's hard to build. It's hard to keep it working. But it really helps once you have it working. All right. Any questions on that stuff before we move on? Nothing?
I'm good.
Okay, Kent just noted that it looks like a spot opened up. If somebody wants to sign up for an exam spot, you can do that. Okay, a transceiver is a combination or a portmanteau of the words transmitter and receiver. Oh, Rob, I didn't I saw that there was a note, but I didn't get to read it. Let's say you go to another area. How do you know about where the repeaters are? Okay, there's a guide called repeaterbook.com. There's also an app that they have. I would strongly recommend that people actually look at it, because it lists repeaters graphically as well as by distance and direction. So that's one of the first things I do when I get to a new place. I open up Repeater Book and I look and see what repeaters are close and whether they're open and how to access them. Okay, a transceiver allows me to transmit and receive with one box. A transverter is a device that converts one frequency to another. So that might mean that it's 10 meters in and 70 centimeters out. Why would we want to do this? Because sometimes you like using your 10-meter radio, and you can build a device that will convert its receiver and transmitter to operate on a different band. Okay, if you have a handheld transceiver and you want more power, you would use an RF power amplifier, radio frequency amplifier. The SSB CW FM switch on a VHF power amplifier. Okay, well and I know this is going into the weeds a little bit, but I think it's important to note. So, does everybody remember what this thing is called? What is that called?
Transistor.
A transistor. And in fact, this is a bipolar junction transistor. And this is an NPN transistor. Okay, so importantly, with regard to this, the curve of output versus input, remember it looks something like this. We have this area in here that's in the linear range. When you have a switch on an amplifier, which is usually built around a transistor, it allows you to either use the linear range or not care about the linear range. Single sideband is voice. Linearity is very important, otherwise your voice will be all distorted. If you're using Morse code, all you care about is that it's on or off. So you're looking for efficiency rather than linearity. So you would typically run that amplifier in this range. Same thing with FM. All you really care about is the frequency, not the amplitude. So what it does is it changes the starting point of where this amplifier operates in order to make it more or less efficient. If you're operating in single sideband, it puts the starting point right here. If you're doing Morse code, it just basically says we're going to operate way over here. And the same with FM. That's why you have that switch, to be able to select which way it's going to run. Okay. All right. The term to describe the ability of a receiver to detect the presence of a signal, that's like hearing a whisper. If you have sensitive ears, you can hear it very well. That's sensitivity. Selectivity is like when you're at a party and everybody is trying to talk to you at one time. The ability to hear just one person, that's known as selectivity, discriminating between multiple signals. As we talked about yesterday, an RF preamplifier, like you would use for a moon bounce station, you would typically put that as close to the antenna as possible because you can't amplify what is already disappeared. Let's see, which of the following is used to convert from one frequency to another? A mixer is a device that is a non-linear device that if you put two different frequencies into it, you will get the sum and difference frequencies out. So if you have 100 megahertz going in one side and 10 megahertz going in another side, you will end up getting 90 and 100 megahertz, or 90 and 110 out. Preamps, some preamps actually are RF amplifiers on one side. Like if you buy an RF amp, it'll sometimes have like a 20 dB preamp built into it. So the other thing is how is a mixer different from a transverter? A mixer is at the core of a transverter, and it's bidirectional. That's pretty much it. Okay. A circuit that generates a signal at a specific frequency is called an oscillator. And in order to make an oscillator work at a particular frequency, what devices do you think you would use to do it? I'll give you a hint.
A capacitor.
Yep. Capacitor and inductor. That's a tank circuit. A tank circuit is an oscillator. So we're going to feed some of the signal back from the output. And let's see, where would I put that? Actually, we don't even really need to. It has an L and a C, and that makes a resonant circuit 1 over 2 pi square root of LC. That's your resonant frequency. You change this value, you can tune the amplifier. You can tune the oscillator. Pretty cool stuff. By the way, a long time ago, you actually used to have to draw those on the exam when it was a written exam. You had to draw different kinds of oscillators. Don't have to do that anymore. Which of the following describes modulation? Modulation is combining a signal that has information with an RF carrier signal. An RF carrier is just the frequency of the radio frequency wave, 7.020 megahertz. When you modulate it, it puts information on it and makes it more interesting. Okay, symptoms, cures, causes of common transmitter and receiver problems. Okay, radio frequency interference. So we're starting to talk about rules and regulations a little bit here, and how the real world kind of gets in the way of of radio. What can cause radio frequency interference? Fundamental overload. That just means there's a monster signal, like the AM radio station nearby. Right? You've just basically wiped out your receiver's ability to hear anything. A harmonic is a multiple of a frequency. So if I'm operating at 10 megahertz, my transmitter might also be putting out signals on 20, 30, 40, 50, 60, 70, etc. One of the reasons that we actually go through the process of taking a licensing exam is that there is a need to understand how harmonics work. Because even though you may not ever desire to build your own piece of equipment, you are allowed to. So here's our fundamental frequency. This is, let's say, 10 megahertz. This will also put out a signal at 20 and 30 and 40 and 50 megahertz and all the multiples. Those are known as harmonics. So each of those harmonics has to be a certain amount of power, a certain ratio down from the fundamental frequency. How do you think we measure that? What unit of measure do we do to do that?
dBm.
Well, nope, just dB. Because whatever the fundamental is, we just have to be a certain number of times lower. And one of the reasons that we study and have to pass this exam is, again, because we are allowed to build equipment. If we do not understand what it takes to build equipment and meet FCC purity, spectral purity requirements, we can do what with our stuff that we build?
Make a lot of interference for others.
We can interfere with other services that are licensed. So we are given the privilege, even if, like I said, even if you never plan to do it, we have the ability and privilege to build our own stuff. One of the responsibilities about building your own stuff, like let's say you build a car, right? If somebody said you can build a car, but here's the rule book about how you have to build a car and how it has to be safe and how the wheels have to work and all that other stuff, you could do it, right? It's the same thing here. There's a rule that says that all spurious emissions and all harmonics have to be X number of dB lower than the fundamental frequency. That's why we need to understand what decibels are. That's why we go through the process of learning all this. And let's say you go and buy something and it turns out that it was built wrong, right? Let's say you go out and buy a commercial handheld and it turns out that something in there was built wrong and it's malfunctioning. Whose fault is it if you're interfering with someone?
Still yours.
It's yours. Yeah, it's your equipment. You're the one putting it on the air. So you have to understand it, even if you're not the one who built it. Okay, so what should you do if your neighbor says that you're interfering with their radio or TV reception? First thing to do is turn on your own TV or radio and see if it's interfering with yours. One of the most important things that happens is that somebody in your house will buy something and plug it in, and all of a sudden you're listening to the radio and you hear, it's literally sounding like that. Well, I was able to positively identify by turning off all the power in my house that it went away when I did that. I had the radio on a battery. Okay, well, whatever is interfering with me is in my home. Right? Okay. So if if it's something that I'm interfering with, then okay. If my neighbor's house, let's say that they think that I'm interfering with their lights, right? Well, do I have lights? Can I test it out? If it's not interfering with mine, what's different about theirs that's different about mine? So it turns into a game of, you know, maybe it's not your fault, but you still try to fix things. Non-fiber optic cable TV, that would be cable TV in a cable. If you have loose connectors, those loose connectors can leak signals in and out. So you transmit, your TV starts to go a little haywire. The picture goes a little nuts. And that's because you have signal leaking out, leaking into it, because every wire can function as what?
Antenna.
Right. If there's one thing you guys come away with from this class, it's the fact that the high frequency band is 30 megahertz, 3 to 30 megahertz. VHF is 30 to 300. UHF is 300 to 3000. And every wire is an antenna. Okay, what could cause an AM broadcast? What could cause a broadcast AM or FM radio to receive an amateur radio transmission? Well, okay, you can have strong signals outside the band and your receiver is junk. Your AM or FM receiver is junk. And it has minimal filtering, which is what I said can happen if you buy a, let's say, a cheap handheld with minimal filtering. What can happen is that the receiver can have signals that are not even in the band that you care to listen to, but they're getting in and swamping the receiver to the point where the receiver just doesn't know what to do with it. It's overwhelmed and it doesn't work anymore. So, for instance, I used to live near an all comedy station, WJOK AM, and that was a 10,000 watt transmitter a mile from my house. It did not matter what frequency I was tuned to. I always heard WJOK.
There could be worse things interfering with you.
There can be, yeah. um, how can fundamental overload be reduced or eliminated? There's that word again. That word shows up everywhere. What is that word, everyone? Get used to seeing it.
Filter.
Filter. Inductors and capacitors. Tuned circuits. Filter, filter, filter. Filters are used everywhere. They allow us to keep one frequency from impacting somewhere that it's not supposed to, and vice versa. You can use a transmit filter, you can use a receive filter, you can use both. Filters are used everywhere. They're used for audio, they're used for RF frequencies. It used to be that is anyone old enough to remember the Bell system where you rented a telephone every month from the telephone company? I know we did.
Unfortunately, yes, I'm not
Yes.
old.
So, yeah, I do too. Well, we
Parents
had
used
a
to.
rented telephone on the wall. And what happened was, if, let's say, I was a ham radio operator, which I was, and when I transmitted, it made the telephone go, which my parents did here, the phone company would come out and install a filter on the phone to keep that from happening. They would actually do that.
Hey, Scott?
Yeah.
Yeah, it's Kent. If you got DSL service, well, I'm trying to think. No, I'll take it back. Yeah. Never mind.
Okay.
I don't want to muddy the waters.
Okay.
See you later.
Which of the following can reduce overload of a VHF transceiver by a nearby commercial FM station? Well, there's that word again. Filter, filter, filter. If you want to reject a certain range of frequencies, you install a band reject filter. You might notice a common theme in all of these questions. If something in your neighbor's home is causing harmful interference to your station, well, first of all, make sure you designed everything right. Second, work with your neighbor to find it. And then, this is the fun one. Inform your neighbor that you're licensed and the thing that they have is a Part 15 device, which is licensed, but not really. It basically says that it's part of the rules, but if it gets interfered with, oh well. If it interferes with you, oh well, they have to stop using it. You may look at, for instance, your power supply for your computer or your charger, and it says this is a Part 15 device in very, very small print. And that basically says that if there's any interference that stops it from working, it has to be accepted by that device. And if it's causing interference with anything else, you have to stop using it or put a filter on it so that it doesn't interfere anymore. If your FM signal is distorted or unintelligible, your battery could be low, you could be off frequency or be in a bad spot. You could also have multipath. That's a bad spot. A symptom of RF feedback. If you have RF feedback, that again ends up sounding like basically you have RF getting into your microphone cable. What do you do with your microphone cable? Does anyone remember?
Ferrite chokes.
A ferrite choke, yeah. Ferrite choke acts as a filter. There's that word again. Okay, if you're over deviating in your handheld radio, you move further away. That means you're basically sounding distorted. If you're under deviating, you get a little closer. Okay, basic. So, Kent, did you want to take the mic for a minute?
No, not at all. I was just staying connected to
Okay.
listen to the group, and I'm seeing some registrations come in, some being canceled. So I'm just trying to keep the group advised if there are slots that are opening up. We've got two open slots right now for tomorrow.
Ooh, we got 2 open slots. Cool. Okay, which of the following measurements are made using a multimeter? That would be voltage and resistance. Does anybody live close to a Harbor Freight by chance?
I do, like 10 minutes away.
Does everybody kind of love Harbor Freight tools for some things? I mean, I have to
love it
admit,
and you hate it at the same time.
I love hate. Yeah.
yeah, I mean, there are certain things that I really like Harbor Freight for because I don't really feel like spending for myself $400 on a multimeter. However, Does anybody have a $3 Harbor Freight multimeter? I do. Sometimes
Most of the time, that's good enough.
Sometimes they give them away for free. That's
Yep,
right.
got it for free.
I got mine for free as well. Okay, so the thing is about a Harbor Freight multimeter. Notice that this Harbor Freight multimeter is $6.99, right? Okay, the question is, how accurate is it? I would assume not great. The other thing is, it says that it's rated at 250 volts. Personally, I would never use it for 250 volts. If I were wearing gloves, I'd use it for 120 volts. I've probably done that. But, like at work, I use this for my multimeter. Anyone ever seen a Fluke 87?
Yes, they're awesome.
They're awesome. Notice rugged, waterproof, dustproof, IP67, which means you can get it wet. It withstands the leads and the meter are both rated for 1,000 volts. Notice it's also $540. I have one of these at work. The reason I have one of these at work and I don't use this meter at work is because at work I use a meter to often check 480 volts AC, right? And I don't feel like, even though this says actually it has a 250 volt AC range and DC, 250 volts. So this is rated for 250 volts. So they say. Are these leads good for 250 volts? I don't really know. But I know that the leads that I get with this meter are going to be good for 250 volts. See, look, they even show an electrician standing there testing things. I would feel okay doing that. That's why it's important to know the thing that you're measuring and understand what's safe and what's not. We do work with some high voltages in this hobby. So, things that we use a multimeter for: voltage and resistance. To measure electric potential is also known as electromotive force. That's measured in volts, so we would use a voltmeter. How do you measure a voltage? You would put the voltmeter in parallel. How do you measure current? You put it in series. Another thing, though, is that if you look at how an ohm meter, for instance, actually works, notice this resistance setting. Every voltmeter has an ohm meter. Every multimeter has an ohm meter built in. So in order to measure the resistance of something, what you do is you apply Ohm's law, which means you put a test voltage across it, and that makes a current go through it. And when the current goes through it, you can measure the current. So if I have a voltage, and here's an unknown resistor, and so here's my power right here. And I have an ammeter, which measures the current going through. And I have a voltage, and I measure the voltage over here using a voltage measurement device. If I know my voltage and I know my current.
Send us your picture.
Oh, darn it. It should be there, but it's not. I have to do that first. Okay. Well, that's a horrible picture. I'm going to redraw it. So here's my voltage. That's my battery. There's a voltmeter in each one of those. There's also a voltmeter that is measuring the battery voltage. There's an ammeter that's measuring how much current is flowing through my unknown resistor. And by Ohm's law, E is equal to IR. And the meter does the calculations, and it magically comes out with the value of resistance. Now, one thing you can do to blow something up is, let's say that you have it on the wrong setting. Well, if you do that, because this is your meter right here, there's a lot of stuff in there. If I were to, for instance, try to measure something that there was already a voltage hooked up to it, I would get a separate voltage source. I would get the sum of the two voltages, and my ammeter would measure the wrong current. it says, well, I'm only measuring this voltage because nobody would be stupid enough to test. Notice I say that because I've done it. Nobody would be stupid enough to test out a resistor in a circuit that already had power because they should know that it would be wrong. Well, and then it comes up with the wrong resistance. The other thing you can do like that is you can blow up your meter, depending on whether or not there's a fuse in it. Um, you can also blow the fuse in the meter, which I've also done embarrassingly several times.
Yeah, and one thing to note is a lot of the cheaper multimeters, the ratings is like 10 amps or less.
Yeah.
For current, and so a lot of the stuff you're going to touch are going to be higher than that.
Yeah.
So it does take a higher amperage.
Yeah. So that can damage it using the wrong setting. Which of the following precautions should be taken when measuring high voltages? Ensure that everything is rated for use at the voltages to be measured. If the voltage is too high, you can get an arc that happens inside your meter. An arc causes rapid heating and expansion of gases, which can blow your meter up in your hand.
Lets the smoke out.
Yeah. Well, but it does more. It'll actually have parts flying at you. So you don't want to do that.
Hey, Scott?
Yeah.
Yeah, I always like to mention, thinking about this for a second, when this situation occurs, what's happening is you're taking a solid, typically copper, and it's changing from that solid form to basically a gaseous state instantaneously. So think of the blast force that's going to be associated with that, because it's got to expand. It's like water expands into steam, but it's horrible.
I want to say 20,000 times.
Yeah,
so?
It is so dangerous at high voltages and currents, and that's why all the special. When you see guys work on electrical lines and whatnot, they're wearing so much protective gear and special insulated tools and all of that. So it's a very serious condition, and you really need to have some awareness of the potential for arc flash.
Yeah, arc flash and arc blast, both—they're bad. Yeah. Okay. How is an ohm meter connected to a component? In parallel, never in series. When measuring in-circuit resistance with an ohm meter, ensure that the circuit is not powered. Like I said, I've made that mistake, and the answer is usually wrong. Okay, knowing that an ohm meter contains a battery and an ammeter and uses Ohm's law to figure out what the value is, if you connect an ohm meter across a big capacitor, what will happen is the battery will slowly charge up the capacitor until it's full, and then it won't have any more capacity anymore, and the current will drop to zero. So your resistance will start looking like it's low, and then it will change and go to infinity. As it does that, you say, oh, there's a capacitor in there. So increasing resistance with time. That's how you know that there's a big capacitor in there. Instrument used to measure electric current is an ammeter because it's amperes. A voltmeter would be volts, which is electromotive force. An ohm meter would be ohms because it's resistance. When configured to measure current, how is a multimeter connected? In series. If you do it wrong, you will blow the fuse in your multimeter and then have to go buy another one if you're lucky. So be careful. For high currents, actually, we tend to often use something called an inductive ammeter. So what's an inductor, everybody? What's an inductor?
It's a wrapped wire around a core.
Yep. So if I have a piece of wire and I wrap a coil of wire around it, that will basically capture part of the magnetic field. So I can have a big current flowing through a coil and be able to measure it indirectly. I greatly prefer to do that, especially if I'm looking at something that's like 80 amps. I really don't want to break it. Yes, that is magnetic flux lines. We never use acid core solder, ever, 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 ever. Acid core solder is for plumbing. It will eat your circuit board. The appearance of a cold tin lead solder joint is called a cold solder joint. It's called cold solder joint, and it looks really bad. A nice solder joint looks nice and shiny and clean. Okay, so now we are into the home stretch. FM operation. Type of amateur station. This is really about rules and regs. Type of amateur station simultaneously retransmits a signal of another one is called a repeater. Notice the word is automatically. A repeater works automatically. There are three types of stations that work automatically. A repeater, an auxiliary station, which is like a forwarding station, which connects one piece of equipment to the other. And according to Kent, we have 3 additional slots available if anybody wants to sign up. And finally, a space station. Space begins at 50 kilometers above the Earth's surface. Anything 50 kilometers or above is called a space station. They can operate automatically. So a beacon, yes, a beacon would also be considered like an auxiliary station. Kent, which one? There's a space station can. A space station can function as a repeater.
I was just reading the chat. Do beacons not automatically send out telemetry? Well, not necessarily.
Yeah.
But yeah.
But they can. They're
They can.
really they're really considered auxiliary one-way transmission stations.
Yes, set stations, yes.
Yeah.
Sorry.
So they're not retransmitting stations. They are the source. They're actually a form of one-way communications. A linked repeater network, that's where you have a backbone connecting multiple repeaters together. In Oregon, we have a repeater system that has roughly 50 repeaters connected so that if you access one, your signal is transmitted over all 50 of them around the state. Repeater offset in the 2-meter band is 600 kilohertz. Repeater offset in the 70 centimeter band, this is all just memorization. That's plus or minus 5 megahertz. So 446 would be to 441 because you have to look at your chart and see that on the 70 centimeter band, it goes from 420 up to 450. So if your repeater is at 446, it would have to go down to 441. If it's at 448, it would have to go down to 443. And in fact, it does. And unfortunately, there is no other way to know these frequencies other than to really memorize them. The more you use them, the more you'll know. The more comfortable you'll be. CTCSS is is essentially it's a system by which you transmit a subaudible tone along with your voice that operates as a key for the repeater's receiver to accept your signal. Continuous tone carrier squelch system. There we go. If you have the wrong CTCSS tone set or the wrong DCS sequence set or the wrong offset, this happens all the time on repeaters, then you will not be able to be heard. Now, notice this thing called reverse. If I am listening to a repeater and I hear somebody very weakly on the same frequency as the repeater would be, that is telling me that they are transmitting on the wrong frequency. I can listen for stations that are on the wrong frequency by hitting the reverse button. I can listen on the repeater input to hear if somebody is there and isn't, for instance, transmitting on with the right tone. Like if I can hear their signal there, but they're not getting into the repeater, I know that something's wrong in their setup. FM transmission can be distorted on voice peaks if you're talking too loudly. That would be a symptom of over deviating. Another way to call another station, if you know the other station's call sign, KL5T N7JI.
KL5T.
That's it. You say the other station's call and then your own call. And to answer, notice what Kent did. He just gave his own call sign. If I was just listening, I'd say N7JI listening, N7JI monitoring, something like that. Transmitting and receiving on the same frequency is known as simplex as opposed to duplex. It's called simplex. Why are there simplex channels designated in the band plans? Okay, so notice this band plan. Some of these are listed as simplex frequencies. Notice this pink is called FM simplex. The reason those exist is because not everybody needs to be using a repeater all the time. If you and a friend are half a mile apart and you're on hilltops, it's fine. You don't have to tie up a repeater unless you want to because you expect to be talking to somebody else. But if you're just having a conversation between the two of you and nobody else really needs to be involved, there's no reason you shouldn't use a simplex frequency. A repeater is a resource, so not using it if you don't need to frees up the resource for somebody else. The national simplex calling frequency is 146.52 megahertz. That's just memorization. Everybody's got it programmed into their radio. If you're on the high frequency bands, for many years, this was not a question that we really had to worry about a whole lot because, okay, you had, for instance, 10 meters, single sideband, that little blue swath right there. Okay, you had Morse code here in the green swatches, but most people who will get licensed today with a technician license don't go out of their way to learn Morse code immediately. So the only place they could really go was this little blue swatch between 28.3 and 28.5. For about the last, 8 years, there was nothing there most of the time. But now, because 10 meters is wide open many days, there's a lot of local stations. There's a lot of DX on there. And so this has actually become important again, at least for the next year or two. CQ means I'm looking for anyone. Before calling CQ, you make sure that you have privileges on that particular frequency. You make sure you have privileges on the frequency because you can't transmit where you're not allowed to transmit. Then you listen, and make sure that there's nobody there. And then you ask if anybody's there because you might not be able to hear them anyway. Until you ask, they might be listening to somebody else and you can't hear the other station. They might be in the middle of the conversation, and by calling CQ right on top of them, you've just interfered. Inadvertently, but you've done it anyway. So how do you respond to a station calling CQ? CQ, CQ, November 7, Juliet, India, calling and bye. Anyone? Is anyone going to answer me?
KL5T.
Okay, so Kent just told me that he's there. Thank you, Kent. KL5T, N7JI. Good to hear you, Kent. Over.
Yeah, N7JI, thanks for the call. Good to hear you today.
All right, well, I'm going to sign. Have a good day, Kent. N7JI.
Yeah, 7-3, Scott. See you next time. KL5T.
That's a conversation. That's it. It's just back and forth. Notice the call signs indicate who you are and who you're calling. Okay, when identifying your station, you have to identify every 10 minutes and at the end of the transmission. Those are the rules by the FCC. Every 10 minutes and at the end of the transmission or end of conversation or end of communications. If you're doing a test transmission, the easiest way to do it, I find, is just use my own call sign because that tests it out and it identifies it. So you have to identify the transmitting station. No transmission can be made except for controlling model craft without an ID. And that's a pretty esoteric thing. There's only really one exception to the rule. QRM is interference from other people. QSY means I'm going to change frequency.
Got it, if I may.
Yep.
Yeah, QRM. Two of you you'll hear a QRM and QRN. QRM, M for man-made. Man-made. QRN, natural interference, like lightning strikes and that sort of thing.
Static crashes. Like 75 meters in the summertime. A band plan beyond the privileges established by the FCC. The FCC does not go, for the most part, into the minutia of specifying what is what here. They just don't want to. The FCC basically on the, let's say the 70 centimeter band, they specify your transmitting boundaries are 420 to 450. Within those frequencies, unless it's actually written into law because somebody asks us to do that, all of these different things that you can do per the band plan are not written in stone. The only thing that's written in stone is that you must stay inside the sideline. 420 to 450. So how do you do that? Everybody, how do you do that? How do you stay inside the lines?
Don't go near the lines.
That's one of them. What's another way to stay inside the lines? If you are going to go near the lines,
check before you're transmitting.
Check before you're transmitting. Let's say the band you're on goes from 7.000 to 7.300, and you are transmitting in lower sideband. What does your lower sideband signal look like if this is your center frequency? Is it above
broadcast in the middle
or below?
Yeah.
We don't broadcast. Remember, we transmit. We never broadcast. That's in the rules.
Yes.
If you're on lower sideband, which side are you on, the left or the right?
The left.
The left side. So I could see my lower sideband signal, and it would be over here. Am I legal or not legal? Even if I tune the radio all the way to 7300.
You're legal.
Yeah, no, you're legal because your signal is entirely inside the band. So now what I'm going to do is draw this again, and we're going to pick a different band, 14.000 to 14.350. On that band, we use upper sideband. So here's my center frequency, plus, minus. Which side is it going to be on, the right or the left?
Right.
Okay. How wide in kilohertz is a single sideband signal? I heard 3 kilohertz. Yep. Why? Yeah, it's 3 kilohertz. Okay. And this is 14,000 kilohertz. And this is 14,350 kilohertz. What is the highest frequency I can tune my dial to? This FC, this is my dial frequency. What is the highest frequency I can tune to and still be legal?
11,350.
No, say that again.
Was it 11,350? I'm sorry. Yeah.
14.347, because my signal will look like that. And every part of my signal needs to stay where? Inside the side rails. Yep. My whole signal has to stay inside the band, which means that this is another way that ham radio is different than any other service. If I am on FRS or I am on GMRS and I go to channel 22 or channel 4 or channel 7, am I legal? I don't have to know what the bandwidths are. I don't really need to know what the deviations are, because they have said that I can use channel 1 up to channel 22. Those are predefined frequencies. That is a channelized service. In amateur radio, 14.000 up to 14.350, where does the FCC say we have to tune?
Inside that.
They don't say. There are an infinite number of frequencies anywhere in this range that we can tune to, so long as the only requirement is that our signals stay inside the band. That is it. We have the most flexible service of any that exists because of that. We can tune anywhere we want. Yes, and the only place we have to stay the only place we have channels is on the 60-meter band. And that's because we have to interoperate with other services. Everywhere else, we basically have free reign inside our bands. It's pretty cool. It's pretty unique, actually.
Scott.
Yes.
I've got a little PowerPoint slide. I'm not ready, but I'd like to show in a moment to illustrate the power and our allocations on ham radio. It's really is illustrative. Would you mind if I dig that out and pull it up, and I'll let you know when it's ready?
Sure.
It's really cool.
Okay, let's see. When two stations transmit on the same frequency and interfere with each other, who owns the frequency? The answer is nobody. They have to figure it out. They could both move. One could move.
Or an arm wrestling contest.
Yeah, nobody owns a frequency. Okay, public service. Amateur Radio Emergency Service is an organization that is run by the American Radio Relay League, where people volunteer for emergency communications using ham radio equipment, licenses, and the knowledge that they have. The difference between that and RACES, which is the Radio Amateur Civil Emergency Service, notice that word civil, that means that the government is involved. So basically, it's the same thing, except that you have to register with a civil defense organization. So ARES is private, RACES is public. RACES is government. What is RACES? It's defined in the Part 97 rules. ARES is not. Civil defense, part of governmental operations. Typical duties of a net control station. The net control station calls the net to order and directs communications and traffic. Traffic is information going across a net. A net is short for a network. When you participate in a net, you only transmit when you only speak when you're spoken to, because again, there's only one net control station. The net control station controls everything and needs to be able to hear important stuff and disseminate important information. So the net control station has the ball. Unless they give you the ball, you don't do anything. Unless there's an emergency. Traffic is information or messages exchanged by net stations. Good traffic handling means that you are really, really, really precise. That you repeat everything that you hear, you write it all down. If somebody hands you a message, you make sure that it gets sent accurately and you verify that it's been sent properly. This is one of the reasons that we use the phonetic alphabet, because there are a bunch of different ways, for instance, to spell a lot of different names. Like Shamburic. I know that it's Sierra Hotel Alpha Mike Bravo Uniform Romeo Echo Kilo, right? There could be different ways to spell that. I made sure by using phonetics that it was spelled correctly and somebody could understand it. In the preamble of a formal traffic message, the preamble has all the information needed to track it. Phone numbers, names, addresses, email addresses. Check is basically the same thing that we do in digital communications, where we send a checksum. After the message is over, we include the number of words or word equivalents. If the message is "I am going to the zoo," 6 words. I'd say 6 words. But let's say the other person got "I am not going to the zoo." They said, "But I got a number of 6." Well, something was wrong there. So the check is basically the verification that the right number of words were sent. When do the FCC rules not apply? The FCC rules always apply. That's kind of an easy one. Are you ever allowed to transmit outside of your operating privileges of your license class? Yes. This is important. In immediate safety of human life or protection of property. Someone's about to die or the dam is about to burst and flood an entire town. Those are reasonable exceptions to the rule. Amateur satellite operation. If a satellite is passing overhead and it is operating on VHF, technicians can operate on any VHF band, even if the signal is then retransmitted to HF where you don't have privileges. That's okay. The satellite did that, not you. You transmitted your signal where you were legal to do so. So you can talk to the International Space Station. UV mode, that's UHF, VHF. That means the uplink is on UHF, which is 70 centimeters in this case, and the downlink is on VHF, which is 2 meters. Where it is, that's typically going to be published within the band. Some satellites also use single sideband, FM, CW, and data. If you're going to be talking through a satellite, you really want to listen to yourself down on the downlink to make sure that you're not like super loud. And the way you do that is to make sure that when the satellite sends out a beacon saying, "I'm here, I'm here, I'm here," you don't want to be louder than the beacon. So if that's the case, you turn down your microphone gain, turn down your power. LEO stands for low Earth orbit. A satellite beacon contains status information about the satellite, what the onboard temperature is, what the altitude is, what the transmitter power is, what the battery power is like. So, who can receive telemetry from a space station? Again, a space station is anything 50 kilometers up or higher. And the answer is anybody, because anybody can receive pretty much anything. You don't need a license to receive. Satellite tracking programs. These use something called Keplerian elements. And what they do is they basically give you a map and tell you graphically, in a lot of cases, where a satellite will be and when, how high it's going to be above the horizon, where it's going to show up, where it's going to disappear. If you go to AMSAT, AMSAT, you will see they have a ton of a ton of satellite tracking stuff, and they track the 100 or so amateur satellites that are up there, and amateur satellites that you can use. They track the International Space Station, and from there you can figure out where the space station is going to be and when it's going to pass over. And there's actually a ham station on the ISS. I have actually made contact with an astronaut before. It was really cool. Doppler shift. Satellites are moving at, depending on how high they are, the low Earth orbit satellites are typically moving at about 17,000 miles an hour. And the same way that you can hear the pitch of a fire truck change as it gets closer to you and drives away, the pitch changes. The color of the light being sent out by a satellite will actually change when it's approaching you and moving away. That light is in the form of radio frequency energy, and at the speeds that it's moving, which is 17,000 miles an hour, it is enough to actually change the received frequency that you will tune to. And as it's moving away, it'll stretch it out. Similarly, you have to know that if something is coming toward you, the satellite's coming toward you, you actually have to tune your radio to a lower frequency because it's getting closer and it will compress the waves. Spin fade, that's when the satellite is rotating. Most satellites do rotate. As it rotates, the signals start to fade a little bit. All right, now we're into operating activities. Contesting, one of my favorite things to do. Making as many contacts with as many stations in as many places during a specified period. That could be an hour, that could be an entire weekend. It's a blast, it's competition. I like competition. During a contest, you only send the minimum information needed. 5903. That's it. That's your call sign and your signal report. Unless you know the other person really, really well, that's all you send. A grid locator. One of the things that I sent out was a grid locator map, and somebody commented, "What in the world is that?" So a grid locator is there's something called the Maidenhead Grid Square System, and the entire world is broken up into 1 degree in latitude by 2 degrees in longitude into, rectangles. And each of those is then broken up into 10 by 10. And each of those is then broken up into 24 by 24. So what it allows us to do is focus in on one particular place. So CN84 is where I live. CN84 is that particular section of Oregon. And I am actually in CN84LA, which is way down here toward the bottom. So that basically allows somebody to log where I am and point their antennas at me very accurately.
I think it actually goes out to 8 elements too, Scott.
Does it even go more?
Yeah, it does.
I've never used that. um, to find sources of noise interference or jamming, we use radio direction finding. Directional antennas, notice directional antenna. Hidden transmitter hunting is practice for radio direction finding. Find the jammer, find the interference source. IRLP, the Internet Radio Linking Project. So, voice over internet is how we are talking right now. That is how telephones work. The analog signals are converted into digital. Those are then switched from place to place at breakneck speeds over long distances, so long as the internet is functioning. That is called voice over internet protocol. IRLP is a hybridization of ham radio and the internet. Echolink. Echolink is something that is a phone app or a computer-based app where you register your call sign and provide proof of license, and you are given an account that allows you to connect through the internet to repeaters and other ham stations all over the world. Let's see. How do you establish a link to IRLP? DTMF is touch tones. If you're on a repeater, you punch in a bunch of touch tones, and that keypad on your radio, if you're transmitting, sends touch tones. A gateway is a station that connects other stations to the internet. And now we're into the driest part, but very important, called rules and regs. And I think we're going to run over by a little bit, but I think this is like really important. If anyone has to go, you can always catch up. Okay, the FCC runs amateur radio in the United States. There are, again, we did this yesterday. Look at the FCC Part 97 rules, and there are the 5 reasons why we exist. Notice advancing skills in the technical and communication phases of the radio art. If you think that radio is dead, radio is not dead. We are actually continually coming up with improvements to it. We use radio all the time in our lives. And you know, it's funny because Heinrich Hertz, who discovered radio waves based on the work of Maxwell, after he discovered Hertzian waves, which are now known as radio waves, he was asked, being a scientist, can you think of anything these might be used for? And he said, I can think of nothing whatsoever. They are merely what was it? They are I forget what it was exactly, but basically it was like an oddity, and we would never find a use for them. So, and that's why we have engineers. Engineers are good at finding use for things like that. A space station is anything more than 50 kilometers above the Earth's surface. Willful interference is never permitted. So you can interfere with somebody if it's accidental. You should probably stop if they tell you you're interfering with me. You can never interfere with somebody intentionally, even if they really, really tick you off. Transmit and receive channels. Okay. So notice this volunteer frequency coordinator. This is even beyond a band plan. So if you look at repeater book, you will see that there are frequencies that have been coordinated for use by certain repeaters, right? This pair of frequencies has been allowed to be used by this particular call sign. The volunteer coordinator, which is selected by people within a given area, like the state of Oregon, who are eligible to own repeaters or auxiliary stations, that person, it's a very thankless job. Their job is to keep the peace between all the different repeater owners that want to use those frequencies. And actually, being a trustee, our repeater was handed over to me about 6 years ago, but they never relisted me as the contact person with our coordinator. So I got a forwarded note that said our coordination, which has existed for, I don't know, 45 years, was in danger of being taken away and given to somebody else unless I updated our information. It took 3 minutes, and now we're good for many more years. But basically, that coordinator is responsible for making sure that people who want a pair of frequencies to use can get access to it. Frequency allocations and power limits. Okay, this is the only way to know this stuff is to memorize it. 6-meter band. 6-meter band is 50 to 54 megahertz. That's it. So knowing that, you then know that, okay, 6-meter band includes 52.525. Just got to memorize it. 146.52 is clearly in the 2-meter band. 2-meter band covers 144 to 148. Where do you have phone privileges? Take a look at the band plan and say, okay, well, that blue hatch right there says novice and technician voice. Novice is the license class even below technician. It's the entry level, which you can't even get anymore. You haven't been able to get a novice since like 1994, 97, but there are still people who have novice class licenses. Once you have it, you don't have to change it. You don't get grandfathered into something else. Where do you have phone privileges? On the 10-meter band. What are your frequency privileges? Well, it says so right there. 28.3, 28.5. Where can single sideband phone be used in amateur bands above 50 megahertz? Well, here we go. Single sideband phone, SSB weak signal. It's that olive green. Well, shows up on every band, which means you can use it at least somewhere on every band. Which band segments are limited to CW only? Well, you got this one, which is red, and this one, which is red, and actually this one, which is red. But remember I said that very few people actually get on 222 because there's very little equipment for it. So that's not even really considered in the question. So there you go. 219 to 220. Well, okay. So this is so weird that it's not even on this band plan map. This band plan starts at 222. This is such a weird band that it doesn't even show up. And the reason it doesn't show up is because it's fixed digital message forwarding systems only. Again, that was a thank you, United Parcel Service thing. Why shouldn't you set your transmit frequency to be exactly at the edge? Well, okay. Modulation sidebands don't go beyond. Your transmitter frequency might not be accurate. I have an ICOM 7300, and I was told that it was 100 hertz off. That might not be a big deal, but somebody then said, well, there's a calibration procedure for it, and it's really easy to do. And I went and did it. And now I'm right on within, I don't know, 10 hertz or something. And that's on a brand new radio. So how are U.S. amateurs restricted in segments of bands where the service is secondary? Secondary means we don't have primary privileges. If we don't have primary privileges, that means that we can't interfere with somebody else at all. And in theory, they can kick us off, like the U.S. military on the 70 centimeter band. If they really want to, they can say, we need to use this because they're primary and we're secondary, and we need to stop operating. Okay. Peak envelope power for technician classes using frequencies above 30 megahertz. That number is not a mistake, everyone. That's why you're taking a class. You can do a lot of harm with frequencies above 50 megahertz at 1500 watts. On the HF frequencies, you can use 200 watts. We have 3 license classes that you can get. You can get a technician, you can get a general or an amateur extra. No, I don't know why it's called amateur extra when the others are not called amateur technician and amateur general. It's just one of those things. A license is good for 10 years. That is a license grant. It's good for 10 years. As soon as your information appears in the FCC ULS license database, you are good to operate if it says active. You can have one license grant, one station license grant. That means you can basically have one call sign. What proves that your license is valid? If it says it appears in the database and it's listed as active, you have a license. They used to send out pieces of paper. They stopped doing that a good number of years ago.
There's still a secret way you can get that, but it's obscure.
Who can select a desired call sign? Okay, so you get your license. You hate your call sign. It's awful. It's KX7UQX, right? If you do Morse code, that's a horrible call sign. So I hate my call sign. I want a different call. So the first call sign you get is sequentially allocated. You don't have a choice. Beyond that, there's something called a vanity call sign. You can pick any call sign that has not been allocated so long as it is in the class of call signs or the group of call signs that is valid for your license class. If I have an extra class license, no, a GMRS cannot get a vanity call sign. If I have an extra class license, I can get a 2x1, which is like NA7T. I can get a 1x2, which is like NT7 or N7TA. Those are both extra class call signs. Not in Alaska, but in the lower 48, you can get a 2x2, like KJ7TM. However, as a general or a technician class operator, you can only request a 1x3 or a 2x3. So KF1XXX, K1XXX. Those are both valid. And anybody can request a vanity call sign. And please understand that all call signs in the United States start with the letters K, W, N, or AA through AL only. We live in the world. The world has lots of countries. Every country has different call sign prefixes associated with it. We had somebody, I really actually saw this once. He applied for an FCC call sign. He actually sent in the application form, and it was for Bravo Zero Bravo Bravo Yankee because his name was Bobby. Well, that call sign the answer was, sorry, we do not have the ability to grant your call sign because it doesn't follow the format of United States call signs because that call sign is owned by China. So know what you can apply for before going through all the effort of doing so.
But your call sign doesn't change every time. Like we go from technician to amateur extra or whatever, we keep the same call sign all throughout the process, correct?
When you get the form 605 and you fill it out, there's a checkbox that says, do you want to apply for a new call sign? So you can change your call sign at that point. If you really hate yours, you can say, give me another sequential one.
It'll ask if you want to change it systematically.
Yeah. What's the grace period for renewal of a call sign? If your license expires, you have 2 years before it goes back into the pool for somebody else. If your call is expired and still within the grace period, you may not transmit until that database says active. If it doesn't say active, it's not active. Okay, if you want a club license, a club is 4 members. The assumption is that it's secretary, treasurer, president, vice president. That would be 4 members. So if you have 4 members, you can apply through, for instance, one of the VECs, like Kent, and they will handle your club call sign grant application.
Clarification.
Yes.
You do not apply for a club call through a VEC. You apply for a club call.
Yes.
You apply for a club call through a call sign or a club station call sign administrator, a CSCSA.
Ooh, okay. I did not
So
know
we
that.
are a VEC, but we are also a CSCSA.
Okay. Are all VECs in that category?
No, sir.
Okay.
Only a few of us.
Okay. ARRL is one, right? Okay. Okay. If the FCC is unable to reach you by mail, if they try to send you a letter and it gets returned. Now, this is really interesting. It is important when you apply for a license to put an actual functional address. I have actually because I'm the ARL Oregon section manager, I take the lists of everybody who got licensed in my section. There's about 50 a month, and I send them welcome letters. We hope you join the ARRL. It's a good organization. Even if you don't, we're happy to have you as, we're being a ham in our state. Every month I get, for brand new licenses, I get 2 or 3 that are returned to me. I have no idea why. They say undeliverable. If the FCC did that, those licenses would get pulled. They say this license is no longer valid. The other thing is email. If they try to email you and it gets rejected, they can also cancel your license. They need to be able to find you. Some people get mailboxes. Some Canadian citizens have US mailboxes, right? That's okay too. What can result in, we covered that, email address, mailing address. From which of the following locations can a station transmit? Okay, if you have a US license, you can transmit anywhere unless the government specifically says you're not able to, anywhere that is part of the United States. A ship with an American flag is a part of the United States. You probably need to ask the captain, but you are legally permitted without getting a reciprocal license or anything like that from operating in international waters and registered in the United States. Okay, authorized and prohibited transmissions. You are not allowed to transmit anything indecent or obscene. The same thing that applies for broadcast television, broadcast radio, those same rules apply. When are you allowed to transmit using a phone emission? Using music? That phone means voice. Music is music. So when can you transmit music? The only time, although if it's, let's say you're at a music festival or something, or a street fair, and there's music in the background, nobody's going to complain. We don't broadcast, right? Notice it says retransmission of manned spacecraft communications. This actually came from the Space Shuttle program, when NASA used to wake up astronauts and would also at the same time rebroadcast all of their communications over the over amateur bands. So at that point, they would wake up the astronauts using music. That music would go out over the ham bands. It's like, wait a minute, why is there music going out over the ham bands? That's why we're allowed to do that. We typically cannot do that. NASA, on the other hand, can. When are you allowed to transmit messages encoded to obscure their meaning? One of the general rules about amateur radio is that we are non-commercial. Another one is that we don't encrypt anything. We're not allowed to obscure the meaning. That means we can't have like secret code words or anything like that. Even if that's just, a word that no one else knows. We're not allowed to do that either because it obscures the meaning. The only time we can do that is when we're transmitting controls to space stations or radio-controlled craft, because we don't want somebody taking it over and crashing it into the ground or running a remote-controlled car off a cliff.
There are a lot of heated discussions that come about because of this specific rule.
When you used to fly RC aircraft?
No, when it comes to the notion of reason, are you encrypting to obscure the meaning of the message, or are you encrypting to control access to the system? Anyway, that's a long discussion.
With which countries are licensed stations prohibited from exchanging communications? Now, it should be pointed out that the only time that a government the only time that hams in a particular place cannot talk to hams in another place is if the government tells the ITU, which is a branch of the United Nations, we object. For instance, North Korea actually has not done this, to my knowledge. They just don't have any hams in North Korea. However, Yemen has. There was a group of Italian hams in Yemen a few years ago who went on a de-expedition to Socotra Island, and they were prohibited as part of their licensing to operate in Yemen. They were prohibited from talking to any stations in Israel because they're still at war from, I believe, 1967. And as a result of that, Even though they could hear each other, they were not allowed to talk to each other, and they could not make contact. In which of the following circumstances can the control operator of a station receive compensation? The only time you can do that is when you're teaching. So if you're a classroom instructor at an educational institution, you can still earn your salary and utilize amateur radio for part of your educational, for part of your curriculum. When can you use amateur radio to notify other hams of the ability of sale equipment for sale or trade? If you don't do it on a regular basis, you're basically not running a commercial business because we're a non-commercial service. That we cannot do anything that has a pecuniary interest, which means we make money at it. We're not allowed to do that. And we can only do it if it has something to do with amateur radio or something loosely to do with amateur radio. You know, you want to sell a computer that could be used in a ham station. Yeah, that's probably okay. You want to sell a couch for somebody to be used in a ham station. That's a little bit harder sell. Now, if it was a couch with a ham radio built into the cushions, okay, that's a little more plausible.
Where can I buy that?
I don't know. Maybe there's a market for it.
Starting to sound like it.
Yeah. How does the FCC define broadcasting for the amateur radio service? That would be transmissions intended for the general public. We typically do not do this. There are one-way transmissions that is similar to broadcasting, except the intent is that it's not typically for the general public. This includes Morse code practice, and this includes bulletins that are specifically designed for consumption by the amateur radio community. So no broadcasting, but we can send beacons. A beacon is a one-way transmission. It contains information about propagation. Okay, if you can receive it, then you know that it's okay. You know conditions are good. That would be a one-way transmission, but it's not a broadcast. When can we help with broadcasting, program production, or news gathering? There's that thing again. If you ever see immediate safety of human life or protection of property, that's going to be the answer. The FCC rules are very lax. You might still have to explain, but the FCC rules become somewhat lax when it involves using your radio to save a human life or to prevent, severe destruction of property. Now, if you have a cell phone and it works, you should probably use your cell phone because then you won't have any explaining to do after the fact. So we are allowed to, this is really what we do, communications incidental to the purpose of the amateur service and remarks of a personal character. For people my age, that turns into, oh my God, I have a doctor's appointment coming up. Man, I really don't want to go. My sciatica is acting up. I used to laugh when I used to hear that on the air. Now I don't laugh about it anymore because I'm that person. When can you transmit without a control operator? Never. There's actually two different things here. There's a station license and an operator license. A station license licenses the equipment. An operator license licenses the person to operate a station. Sometimes they are the exact same thing. Sometimes they're not. A club station can have a call sign and it has a trustee that is technically in charge of it. But if somebody without a license walks into a club station and says, I'm going to use a club call sign, that is not permitted because the club station has no operator. It has no privileges because there's nobody in control with a license.
Unless there's a control operator right
well,
there.
But I didn't get there yet.
I know you did.
But
so
who does the FCC presume to be the control operator of a station? That would be the station licensee, unless it's a club station, in which case somebody walks in and says, here's my extra class license. Then the club station can operate, assuming that the trustee has an extra class license. Then the station can operate with extra class privileges. If somebody, let's say, is on the extra class part of the band and there's an extra class control operator at the station, that person walks out and somebody with a technician class license walks in and then is the control operator, it is no longer legal for that station to be operating in the extra class band because there's a new control operator, and that control operator's privileges are then assigned to the station. This will all make sense the more you operate. When the control operator is not the station licensee, such as in the event of a club station, who's responsible for proper operation? And that would be both people, control operator and the station licensee. If a repeater inadvertently retransmits communications that violate FCC rules, somebody gets on your repeater, which happens, and without a call sign, without a license, decides to start cursing on your repeater, it's actually not your fault because the repeater is operating in automatic mode. It is retransmitting everything it hears. And the control operator of the originating station, who might be unlicensed at that time, is responsible. So the FCC can go after them for that. It might be my job as a trustee or an operator to, if I have codes, to shut down the repeater and make sure they can't use it anymore. And there are usually back channels, back frequencies for shutting down a repeater.
There has to be means to shut it down.
What determines the transmitting frequency privileges of an amateur station? And that is that, again, the class of operator license held by the control operator. Control operator is responsible for what is happening, and their privileges transfer to the station. When can a technician class licensee be the control operator of a station operating in an extra class band segment? This is exactly the same thing that I just said. The answer is at no time. Who can be the control operator of a station communicating through an amateur satellite or space station? If you are allowed to transmit on the uplink, you are legal to do so. Okay, a control point, the station from which control is achieved. Okay, I have a handheld radio right here. I have a handheld radio. This push to talk button, that is the control point. I am in control locally from the push to talk button. There are other forms of control. That would be local control. There's also remote control. Remote control is operating something over the internet. That actually happens a lot these days. If you're operating a station remotely, you have to physically be at the control point, which means you have to physically be at the computer or radio running it over the internet. You have to be able to, you have to be there at all times, and you indirectly manipulate the controls. The other thing is that if you are doing so, let's say you're transmitting and your link drops and you lose control, there has to be a watchdog timer that shuts off the remote station so that it basically goes into a safe state. Automatic control, repeater operation is automatic control. And we are into the very last section. You are required to transmit your call sign every 10 minutes and at the end. It's a weird rule. You don't have to do it at the beginning. We have somebody here in our club who insists on using that rule all the time. Fortunately, I know who he is. Everybody else knows his voice, but that's the rule. You don't have to give your call sign at the beginning. An amateur station can only transmit without identifying when using signals to send control to a model craft, like an RC airplane, an RC car, an RC boat. And actually your name, call sign, and address, I believe, have to be on the transmitter so they can always track it back. You have to identify in English. You can have your whole conversation in another language. You have to identify in English. When I was in Chile, even though I was speaking in English or English and some Spanish or very broken Spanish, I had to identify in Spanish. Call sign identification required for phone signals. Well, You can use phone. Phone is the same as voice. So you can use voice, or you can also send CW, which is Morse code. Most repeaters have a CW ID in the background. Phonetics are great because they eliminate a lot of confusion. Tactical call signs, let's say that you're out operating at a public service event and you are race headquarters or aid station one. You'd say aid station one, race headquarters. Those are not call signs, but they can really simplify things. But the rules still apply that at the end of every communication and every 10 minutes, you have to identify yourself with your actual call sign. There are other ways of indicating that you are somewhere else. KL7CC slash stroke or slant can be spoken and identify yourself as being somewhere else or being some kind of special event. A third party, we do this all the time at our local museum. We get in there, we have a licensed operator sitting at the controls of the radio. We have somebody else out in the field using a handheld or a mobile radio. A bunch of kids come in because it's the Eugene Science Center, and we have a lot of kids there, especially this time of year. And we will sit them down and we will give them the information that says, okay, you're not allowed to say anything, weird or funny or anything like that, but just be yourself. And they can talk over the radio as third parties. What they can do is talk with other third parties in the United States. So I could have a kid sitting here with me on the radio and another kid sitting at the museum with another ham, and they could talk to each other because we allow third-party licensed hams, third-party licensed people, third parties to talk through licensees. This is how the military ran phone patches between soldiers and their families during the Vietnam War. Thousands and thousands and thousands of phone patches over amateur radio.
Even up through the early 90s, Scott.
Yeah.
I ran phone patches from Korea.
Yeah, see, and it's still legal. We could still do it today. Everybody has a phone, but you could still do it today. The one thing that's interesting is that Japan, for instance, has 1 million hams, but they are not listed as a third-party licensee with the United States. There's no agreement. That largely comes from the fact that, like European countries, the telecom company used to be owned by the government. And because the telecom company, if they allowed hams to circumvent long distance charges, that would take money out of the government's pocket. So why would they allow hams to do that? So they didn't. And that's why there are some countries that don't have an agreement. And finally, if the FCC comes knocking at your door, I don't know anybody personally for whom this has ever happened. You have to let them in. If they want to inspect your equipment, you have a licensed station. You have to let them in so they can see your station. I told you we were going to be a little late, but that's not too bad.
Scott, can I show this thing?
Yeah. Well, before that, does anybody have any questions? Does anybody have any comments? Clarifications? I'm sorry, that was a lot of information, but we got to cover it, right?
I actually plan on going through the videos probably multiple times, so I appreciate you sending out the recordings.
Okay, good.
Yeah, good question there. How long are you going to leave those recordings up?
I never take them down.
Okay, that's good.
Yeah.
And second part, do you mind if we share with other people that haven't been here and stuff?
Yeah, go ahead.
Okay.
You can give them all the you can give them the whole you can forward them the whole information packet that I sent out too, if you want.
Great, thank you.
Mm-hmm. I know it's a lot of information, but yes, you need a 74% to pass. But the reason I say 85% is that if you are scoring 85% consistently, you're gonna do fine. You figure nerves are gonna make you miss a couple questions. So if you're 85% consistently, you're kind of in the clear, even if you make some mistakes.
And I had a question about.
Whoop.
Sorry.
Okay,
Go ahead.
Sherry.
So I was just also, do you have a study guide for the other exams? For the general or the extra?
It exists, that same study guide. If you look at those, if you look at the KB6NU website, he's the one who publishes those no nonsense study guides, which again are kind of lightish on the theory, but they cover everything really, really thoroughly. You know, every question is in there. He has them, and the technician he sends out for free is kind of like a gift to the world. He charges a little bit for the general and extra.
Okay.
But I have taught a general class from the general class guide.
Okay.
And it kind of flows similarly. It you know, everything is covered.
Thank you.
Why do you need a ham radio license for flying FPV? You don't. However, if you look at the 5.8 gigahertz spectrum, you will see that a lot of the FPV drones can access without having a license only a couple of channels. And if you only have access to a couple of channels, for instance, I want to say it's like 1 and 2, maybe 3. There's a whole bunch more channels there that you can tune to, but you are not allowed to use legally because they fall within the amateur spectrum in the United States, unless you have a ham license.
Is there an online website or an app or something that you can train for all the possible question for the exam?
Did you get the big? Did you get the big email that I sent you with all of the? Okay,
I can't remember.
Yeah, it's here. It's called. I'll type it out. Ham radio exam tech. This is my personal favorite. Ham radio exam dash tech. By
I think I've missed that.
It exists.
What is it? Is it a PDF?
It's an iPhone and Android app.
Oh, sorry, an app.
Yeah.
Okay.
I recommend using that because there's a section in there that's called take a section quiz. There's like study correct answers and take a section quiz. And the way that it's laid out, it allows you to really drill on one section at a time. It works very well.
Oh. Okay, thank you.
All right, Kent. Take it away, Kent. Oh, we actually looked at this. Are you put? Is this the NTIA?
There we go. So can you see this?
Yes.
Okay, so this presentation, this shows the entire radio spectrum. And I'll just show you a couple things real quick here. So there's ELF through LF, so 3 kilohertz or 300 kilohertz, and we go on up through, there's medium frequency up to 3 megahertz, HF, VHF, UHF, SHF, and EHF. And you see all of these allocations is given by the FCC to all of these different services. So to give you a little perspective, let me do this. So right there, that's where AM broadcasting lives. All right. That's where FM broadcasting lives. That's where TV has slots in those 4 areas. That's where aviation radio lives primarily. Now, here's a couple other services. That's where CB is. So this is band radio, unlicensed service. That's where MERS lives. That's multi-use radio service. That's an unlicensed service. Anybody could do that. It's kind of Not many people know about it, but it exists.
We actually
And that's
covered
it.
we actually covered that in class because somebody knows somebody
Yeah.
who does that.
Yeah, so it's in the
Yeah.
VHF spectrum. It's pretty nice one to know about.
Yeah.
Another one is this, where FRS and GMRS live, up in the UHF spectrum. Okay, and I think that's the last one. Let's see, but we're going to show ham radio here in a second, and this is just going to fly. Okay, here's where we got authorizations in ham radio. But it's not done yet. It's still not done yet.
Wow.
Still not done. So now perhaps this drives the point home a little bit more about why this is such a valuable resource we have as amateurs. We have this massive access to the radio frequency spectrum. And I think this particular graphic for me is pretty telling. So,
and that is also why I strongly recommend that everybody at some point become a member of American Radio Relay League, because they are the only ones who go up in front of Congress and the FCC and fight for us to not lose those. It is it's an almost incalculable amount and of money that those are worth if they became available to commercial interests. Would you agree with that?
Absolutely. The most recent one that I remember we fought for was 3.5 gigahertz. And we did end up losing about half of the spectrum there that we had authority for before. But fortunately, we do operations on 3.4 gigahertz. Two particular entities use that frequency spectrum in amateur radio. One is the Earth, Moon, Earth guys. The moon bounce guys operate on 3.4 gigahertz. That's a little obscure, but it exists, and it's great for experimentation, weak signal experimentation, and whatnot. That's one of the important things about EME is weak signal experimentation. And then we also use it for mesh networking. We actually use some commercial gear that it was built for European applications, put our own firmware into it, and use it on 3.4 gigahertz to do microwave communications under something called ARDEN, Amateur Radio Emergency Data Network. So anyway, we got to keep our eyes peeled on this stuff because the commercial guys are going after it, whatever they can get.
And they have almost unlimited lawyers and budgets.
Yeah. So Scott says, just like any organization you're a member of, you're not necessarily going to agree with every little policy or thing they're going after. But at the end of the day, the ARRL, by and large, represents our hobby, our vocation, if you will, very, very well. And it's worth supporting. It's worth joining. And it's also worth joining your local club.
And what's shocking to me is there are 750,000 hams in the United States, and only about 150,000 of them are members of ARRL.
Yeah.
Which is really kind of amazing because ARRL fights for every single one of them, whether they're members or not.
Yeah.
So join. It's $60 a year.
It's worth doing.
It's $5 a month. It's one nice cup of coffee every month to protect the license allocations. At the very least, protect the license allocations. So anyway, that's my soapbox. Yeah, there was just another one it was about a year ago. There was a group of day traders in Illinois, if I'm not mistaken, that were trying to use a portion of the high frequency spectrum to speed up the communications on their day trading.
Yeah, they're talking about running really super powerful transmitters.
Yeah, like 25,000 watts.
Yeah. Oh, actually, 900 megahertz is under threat
again
right now. Yeah. I don't know if they resolved that, but yeah, they're trying to put some restrictions there. The 900 megahertz authorization is very interesting. There's a lot of, there's open public use, but there's also amateur authorization there.
Well, that's like 2.4 gigs.
Yeah.
And
5.8
and
gigs.
5.8. Yeah.
Yeah.
Yeah. It's ISM, which is Industrial Scientific Medical, which is unlicensed largely.
And in addition to ham radio, we do one of the things that a lot of people are doing. It's very interesting service or activity is LoRa.
Yeah.
Which LoRa you can use unlicensed or licensed. Anyway, there's so many things out there in this hobby. This is a lifelong thing, man. It's really cool, the things that people come up with.
So by the way, Kent, my first license was issued 40 years ago today.
Wow.
40 years ago today.
Believe it or not, I was first licensed in Korea.
I believe that.
1989. Yeah.
Well, you were in the military, right? So,
yep, and it was there was one. Yeah, I got my novice, so that was when generals or above or whoever could anybody could administer. Pretty much anybody could administer a novice exam. Yeah.
So, and I know that Jude, are you still here? I don't know if Jude is still here. I know a lot of people have had to go.
Yeah, I think he said something about leaving. Had to go.
Okay.
He left.
All right.
Yeah.
All right. Anybody else with anything?
Oops.
It was awesome to see a young fellow interested.
Yeah. Well, we didn't even get into the scholarship side of things. I mean, we talked about it a little bit, but somebody did ask a question about that.
Scott, I see a question up there about the conflicting digital formats. Well, they were all supposed to be. There was an agreement signed in the early 2000s by the big guys. Everybody was supposed to follow a singular format. They were going to use DMR.
Yeah.
And they stopped playing nice. So, Yaesu developed System Fusion, and then ICOM, I guess, developed D-Star. Of course, Kenwood's using D-Star as well now.
Right.
So there are the three primary, but now we got other, you got P25 out there, but CSI has come out with this new mode. So I don't know, it's experimentation. Each one of these modes has their own advantages and disadvantages. So you pick the tool that works for you. DMR is cool because you're running 2 streams of data on 1 frequency.
Right.
There's with time sharing, but it's all very interesting. Very interesting.
And it keeps changing.
Yeah.
It keeps changing. Is an open source DMR. Oh, see, that's the thing. Kent, DMR is still proprietary, isn't it?
Well,
kind of.
It's kind of sort of open source to a degree.
Yeah.
I mean, but anybody can build a DMR radio. So yeah, it is kind of open source. I don't know codec stuff or how it works exactly, but it's effectively open source. It's Motorola. DMR is a Motorola scheme.
Okay. Yeah, I know there was
a quick.
Go ahead.
Yeah, I've got a quick question about the ARL scholarship. Like, when you apply, is the license that you have when you apply like dead certain that's what they're going to think of you as having? Or like, if you apply and then get a higher license tier,
if you upgrade, you call them. You write a note to the. Actually, it's not even. It's done over. It's done over Kaleidoscope, which is a web-based service, and you can go in and update your application.
Is that still valid even after the application deadline is through?
Probably not. But if you haven't,
all right.
But it never hurts. It never hurts to update it.
Yeah. Cool. Thank you.
So where are you that you're doing that?
I'm actually a student at PSU.
As in Portland State?
Good for you.
Yeah.
No. Oh, I thought you were going to say
like Penn State
University. Yeah.
Not Penn State. No, Portland.
Actually, Kent, I think there are probably more hams at Portland State than at Penn State.
Yeah.
We have. Do you want to spend a minute, Elliot, and talk about Crazy Andrew's group?
I'm pretty new. I just transferred in, so I don't know the most about it, but I can confirm he is crazy.
Yes, he is. He's great. I love Andrew.
He's so good.
So, Portland State has the Portland State Aerospace Society, or PSAS, and they do ham radio, CubeSats, and liquid fueled rocketry, among other things.
Pretty cool.
And they combine that with all of their engineering programs.
Excellent.
So, and they recommend that their students get licensed.
That's good.
I have had many of them go through this process.
Take a look at HamSci also. If
Oh
you're
yeah,
not familiar with them, that is high level stuff. We're talking this is PhD stuff, man. And you can sit in their Zoom calls and whatnot and just sit there and listen. It's amazing. And we're running one experiment for HamSci, actually right here, my home in Nikiski. We call it Detachment 1 of the Radio Science and Operations Center, which is in Anchorage. And we're running a radio experiment here for HamSci, believe it or not.
And the other really cool thing about it is that the guy who leads HamSci is Nathaniel Frizzell.
Yeah,
he's a PhD electrical engineering professor at University of Scranton.
You know, that's where I'm from, Scott.
Scranton.
Yeah.
I did not know that.
Yeah, so we had Nathan speak to our group, and then we actually, how I found out about HamSci is one of his students there at University of Scranton, who grew up over the mountain from me on West Mountain. We tested him.
Oh, wow.
And that's how I learned. So it all kind of came together. This is a really interesting, very high level group.
Did you ever work at Dunder Mifflin?
No.
You know what I'm talking about, of course.
I kind of do.
Dunder Mifflin paper?
No. Oh, yeah. No. There's a lot of that going on back there. No. Well, it was other stuff. It's gone through a number of owners there.
Yeah.
So,
yeah.
Everything from potlatch to.
Dunder Mifflin paper.
Swanee. Yeah.
Dunder Mifflin paper is from The Office.
That's right. Yes. I'm sorry. That's always funny to me when I see that. Like, yeah, I know that place. Some of the places they refer to in there, yeah, that's real.
Beats Bears Battlestar Galactica.
Yeah.
Funny stuff. Yeah.
Anything else, everyone? There must be some more questions.
When are you going to do a general class?
Oh, you know how hard it is. You know how hard it is.
I got my my vanity call today. So.
Oh, cool. And what is it?
N7JI.
HXR. Okay. Well, it's not a bad CW call either. Nice rhythm.
So yeah, are you going to do any more general classes, or do I have to stick with the recorded one that you sent out?
Oh, it's just, well, you can see that doing a class kind of takes a toll. You know what I mean?
We can buy you a beer.
Yeah. I have to recover before doing another one because then I travel a lot for work, so it's it's not something that I wouldn't do again because I actually like the general class material a lot because it gets into vacuum tubes and stuff like that.
Use the web resources that are, like what Scott gave you, hamstudy.org. Study these question pools. Like on HamStudy, you can flip the question cards over, and there's an explanation for each one of those questions. Those tools are excellent. It doesn't make you an effort. Look, this is something to get into your heads too as well. Scott, you've been licensed for 40 years. I've been licensed for 35 years. Has there been a day in this hobby that you didn't learn something new?
No.
Exactly. So you're never, look, the point is to get the license, and it's just the license to learn. And it's really a good way to learn. You just pass the dang exam, and you're going to be exposed to things that will kind of force you into an area where you will learn yourself. You'll do research. You'll work with others. Do it all the time.
You hang out with the local club. You start doing projects. You start doing operations with them. And the more things you do, the more things you realize you didn't know. Happens every day. Every day I'm on the air. I figure something out that I had and you're like, okay, well, I've spent how many tens of thousands of hours on the air in my life. And I'm still finding every day there's something that I didn't previously know. What don't I know? The problem is I don't know what I don't know until I've realized, oh, I figured out a new way to get myself heard. Wow. I found out that I was doing something that is probably getting in the way. Oh, I never thought of that before. So,
Question, Scott?
yeah.
You know, I got I'm not sure if you can answer it, but the first radio that kind of freebie, $25 or 35, I don't know. Explorer QRZ-1 radio.
Which is actually a decent handheld.
And then many times, when I go in the chat, the nets, they can hear me, but sometimes they say, "Oh, you're just a lot of static, or you're too far away, we can't hear you. You
Okay,
gotta get."
what are you using for an antenna?
I don't have any other antenna.
Well, that's your problem.
Oh.
The
antenna radio would be sufficient.
That was an easy one to solve. Even a quarter wave mag mount on the top of your refrigerator will work better.
A quarter wave.
Just a quarter wave mag mount. I mean, like here, let me go to hold on, give me a sec. Okay, actually I'm gonna keep recording. What the heck? Mag mount, dual band. Everybody see my page? Everybody see my web page? All right, here. Yeah. See this right here? $21, right? Just a little quarter wave mag mount. You got to change the antenna, the connection. This antenna sitting on top of your refrigerator or a mini fridge or the roof of your car or anything that provides anything that provides a ground plane is going to work 1,000 times better unless you're on top of a hill than what you have in your hand.
Oh, and Scott, if you don't mind, can you put the link of this antenna on the chat?
Yeah, I mean, or you just go on Amazon and look up just dual band, any dual band mag mount antenna. You can go to HRO and buy one. You can go literally. I mean, it's there. It's a really long link, but I mean, you just need something. I mean, and if you want to go bigger, you can get something that you can mount on a pole on your roof. Or
I was going to say, go to the one for signal stuff, since that goes back toward ham study.
Yeah.
What about the diamond?
Diamond's fine. They're all fine. I mean, the diamond, comet, those are basically it's a multi-element antenna inside a fiberglass radome. They're fine.
Do you know the model? There are two models, X30, X50, I guess.
Yeah, they're fine.
The only difference I found is the length, the height of the antenna.
Well, and look at the gain measurements.
Right.
The
X50, gain is the only thing that makes an antenna different from the other.
Yep.
Right.
Pretty much. I mean, here. Diamond X50. Here we go. Diamond antenna. Let's just click on that. X50 radiation pattern. Gain 2 meters, 4.5 dB. Okay, there you go. And let's see if we look at base station antennas.
The X30.
X30. That's probably
X30.
what? 3 dB. Yeah, 3 dB. So it's shorter. So it basically has one less element inside that radome. It has one less phased element.
Right.
And here you could go to the bigger one, the X300. Notice that that's even longer. And that's 6.5 dB. So that'll give you a little more gain. The question is, where do you live? What are you trying to talk through? Do you actually need that gain?
Yeah, that's my problem. I don't have a roof. I just have a balcony, so I have to deal with that.
Mm-hmm.
Cheers.
But that's what it comes down to. It just comes down to Picking the antenna.
I'm sorry, yeah, and I'm just looking at the antenna. I see here I see the antenna stands, and I hook up at the end. So basically, you would hook this onto your handheld radio.
Yep.
Correct? Okay.
Yep. And if you get a mobile antenna and it's got an SMA connector built into it, you can just plug it directly in. If it's got a UHF connector, you just buy a UHF to SMA adapter and put it all together. I have bags of UHF to SMA adapters, all kinds of different combinations. You develop your own set of tools. You know, I can adapt anything to literally anything else.
For a handheld, would all those connections be too much loss or no?
No.
No. Okay, thanks.
Right. The biggest problem you're going to have is, the biggest problem you're going to have is how long is the cable?
Using good cable.
Yeah, if you're using good cable, then it's not a problem.
The Mesa and Paolini stuff's pretty good. That I don't know if you played with that. Yes, got good ratings.
Well, the other thing about cable is that you want to be sure, and this is why a lot of people don't like doing that. If you're only going to have a mobile antenna and you have 8 feet of cable, it doesn't matter what it is, honestly. But if you're going to put up an antenna on the roof and you're going to have, a 60-foot cable run, you're going to want to cut it to length and you're going to want to use decent cable. Now, the question then becomes, how do you keep that antenna cable, which is really big and stiff and heavy, from potentially breaking off the connector on top of your radio? In which case, then maybe you do an adapter and you have like a 1 foot long pigtail of, RG174 or RG58 or something like that, where it's so short that the loss is going to be negligible, but it gives you flexibility.
It's effectively a strain relief. It's a noodly connection there, so you don't just break it off your freaking radio.
Yep.
Hey Scott, you mentioned earlier that the N-type connector had a 50 and was it 70 ohm version?
Yeah, it's 50 and 75 ohm versions.
So when could we get in trouble with some of those differences as we're trying to connect these different things?
They're physically different. They're physically different dimensions.
Okay.
If you try to if you try to connect one into the other one, you actually damage it.
Okay, good. So a little dummy proofing built in there.
Yeah. And honestly, most people, like, I have a whole mess of end connectors. Most of them are 50 ohm.
That's funny. That's a really good example of stuff I've never heard. I mean, I knew that existed, but I've never heard somebody present that question in 35 years. That's an example of the new. Like, oh, I didn't realize that.
I didn't realize that. Yeah. Yeah. 75 ohm end connector. Yep, there it is.
And how do you choose the right cable?
Oh, well, you got to consider frequency, range, losses, all of that. Frequency is a big, and power handling capability, right, Scott? Frequency. Yep. You got to look at the cable ratings.
Let's see, loss chart for. Let me see if I can bring up that same chart we had up. Here we go. That's a good one. I hadn't done this one before, but here we go. Notice that this is very similar to what we looked at yesterday. dB per 100 feet attenuation. As your frequency goes up, your attenuation goes up. As your cable gets fatter, your attenuation goes down. So
yeah, but talking about the same RG58 cable.
Yep.
Ken before mentioned a brand which is very famous also on this side of the pond.
Yes.
And I was wondering why should I choose a brand from another? So what's the if I go for an antenna, there's a gain, but for a cable, you're talking about RG58.
Well,
okay, that's it. But
like here's 8X. LMR 400 is basically like 8X. right? That's a land mobile radio, and isn't the Italian stuff, Kent, that you were talking about? That's basically equivalent to LMR 400.
Well, no, LMR 400 is a 400 is a 405 cable.
Oh, sorry,
it's
I meant
larger diameter.
I meant 240.
Yeah, this stuff is similar. Yeah, they're I think it's the Flex 7. Is similar. It's actually a little bit larger, but it is get the Flex. And I have to tell you, I've actually ordered some of these cables for a special projects we're doing from them. And also their connectors are excellent connectors. Even their UHF connectors are semi-waterproof. They're built somewhat like an end connector. They're not very difficult to assemble, but they get some really good waterproofing, inherent waterproofing in the back shell or the back connection on them. I tell you, man, they got a good product. They got a good product.
So just looking at this, notice that RG8X and LMR 400 are in the same class, really. But look at the difference in loss per 100 feet, 2 dB versus 1.3. It doesn't seem like that much, but look up to 440, 8 dB versus 5. The same thing down here with the RG214. RG214 is in the same size category as LMR 400. 5 dB versus less than 3. It's the same basic stuff, but it's a better cable. It's built better internally.
All right. Okay, but forget about that brand. We are talking about plain RG58, right? I bought some cables from Amazon.
Yep.
RG58. I have no idea where it comes from or what kind of brand it is.
How can
I understand that is a good or a bad cable? So what do I have some tools for measure? Do I have something to understand? How can I discriminate?
Do you have a Nano VNA?
Do I have? Yeah, I do have.
Yeah. So if you have a Nano VNA, you can actually connect to both ends of it, and it will put out a pulse, and you can see how much of it makes it to the end at a given frequency. You can actually sweep the cable.
Yeah, Scott, we do that. You know, one of the things you'll find in ham radio, there's a lot of hams they'll get out and you'll have all this old cable laying around, but you don't really know its condition. We actually, in our lab, we'll actually test those old cables using methods like Scott is suggesting to evaluate their condition, see how far they are off of spec. So you can evaluate them.
Right.
But on those cables that you're buying from Amazon, there are hams. There's a bunch of guys that have done reviews. Like you can go on YouTube, and there are hams that have done reviews on those cables, and they'll give you their impression for what it's worth.
Yeah, like I'll occasionally buy a 100-foot piece of RG8X, generic RG8X with cables swaged on from Amazon, and you know the worst thing that happens at the frequencies I'm using it, the worst thing that happens is that one of the connectors isn't crimped right. The cable is going to be okay, you know, but because I'm not running a lot of power, and I'm not, you know, I'll either use it just as itself, or I'll cut it, and the run is not overly long, and for that kind of thing, okay, you know, an extra 0.2 of a dB, I'm not going to fight over it. But if I were putting up a permanent installation, then I would fight over it. So, and as far as nano VNAs, the whole thing about the nano VNA is that, you know, they say, make sure you get an authentic one. What's an authentic nano VNA when they're all made in Shenzhen, China, and everybody has all the plans for everything?
It's an open source project.
It isn't, but it is. It's kind of like the hoverboards. Remember those that came out where everybody sells them and nobody really owns the patent or anything because there is no patent? It was a crowd. It was like a group sourced thing. Somebody, I think, just said, you know, let's make this VNA, but let's make it really cheap out of parts that we can find here in Shenzhen.
There are certainly better pieces of equipment you can buy. We've got some for the club, and it's outstanding. But
yeah, but not for $75.
Not for $75. They're hundreds of dollars. But Man, we use them. We use that thing all the time.
Like a real Hewlett Packard vector network analyzer.
Oh yeah, well, that's crazy. Right?
That's $25,000.
Yeah.
Right.
Yeah. But there's the handheld stuff by what you call it? Oh darn it, I'm not thinking right now. But there are some options. There are some options out there for, between Hewlett Packard and between these cheapo Chinese junk things. Okay. Yeah. There are, if you want to spend a little bit of money.
They're junk, but they still work quite well.
They do.
They do.
They just don't give you like the cool features and things you could do, like with, when you're trying. Well, I'm trying to do a presentation. I can get a really nice graphical output. It makes it easy to change parameters. I can do all kinds of stuff. So
Wriggle. I don't know if Wriggle makes one or not.
Rig experts.
Yeah.
Yeah, they're pretty
The
good.
other one is Wriggle. And I know they do a lot of digital storage scopes and spectrum analyzers, and they're
yeah. Matter of fact, Scott, I just got a grant. I just got an ARRL grant.
Did you? Cool.
For 18 Wriggle. They're just 2-channel digital oscopes.
Really?
Yeah.
That's cool.
Yeah, to pair them with our electronics trainers at the Radio Science and Operations Center. So now you got an electronics trainer, and now we can pair it with an oscope, so we could show a guy, okay, watch what happens when you put this diode into this circuit. You just created a half-wave rectifier, right? And you can see it on the scope.
And how much is a 2-channel scope from them?
It depends. They got different ones. I think it's $230.
Oh, yeah.
Yeah, it's not bad. Sorry, I mean,
anything else?
This is where it goes. This is where it goes, right?
Yeah. Well,
on the subject of cables and stuff, there's what's your opinion on when you're going to cut a cable? Does the length have any bearing on the wavelength or frequencies that you want to talk on? Because some people will say you got to cut it, to match a certain foot, and wrap the excess up, and others say just cut it to fit.
Okay, so I'm going to put something up on the screen here.
That's a loaded question.
That's a very loaded question. You ever seen one of these?
No.
Okay. When you get to your extra exam, you're going to be doing this. All right.
Smith charts.
This is a Smith chart. A Smith chart is a normalized impedance matching calculator. And what it allows you to do is, okay, there's a little bit of magic that happens. And this is too complicated for the class we just did, but not for the extra stuff right now. Okay. So if I have, let's say, a piece of 50 ohm cable here, right? And I have a given length of something else, which is, let's say, 100 ohm cable. And I have an antenna which is connected to the end of it like that. Depending on how long this piece of 100 ohm cable is, we'll call this Z load. There is a mathematical transformation, an impedance transformation that occurs based on the number of wavelengths long that this section of 100 ohm cable is. That allows me to take the load impedance, transform it, and I can get 50 ohms out of it. Or let's say that if I really wanted to, I can also get phase shifting, if I'm not mistaken, out of this. Essentially by making this a different length, it goes back to the Smith chart, and let me cancel that. Okay, so the Smith chart, that center point on the Smith chart is where I want to be. That's going to be my 50 ohm point. And if I move outward or inward, left to right, and then let's say I start at 50 ohms and I go to this right here, it's kind of hard to see. If I go to the 2 times and then I rotate based on the number of wavelengths that I am from or toward the source. That determines where I now am, where these lines intersect, and then I can determine what my new impedance is based on what the impedance of the additional piece of cable is. It allows you to do all kinds of cool tricks, and it allows you to develop a really good understanding of what happens with cable and cable lengths. If you're doing a system where there are a lot of known values, like you know what the frequency is. If you know what the frequency is, you know what the wavelength is. If you know what the wavelength is, you know how much to cut your cable. So let's say that you're building a system where you have, hold on. Let's say you're building a system where you have a single transmitter right here, right? And you come out to a T. And then you come out on this one, and each T is attached to another T. And this comes out to an antenna. And let's say this is an EME array. That is designed for operating on a single frequency. And each of these antennas is 50 ohms. How to determine how long to make each of those cable segments so that by the time they get back here, notice what you have. You have two things in parallel, right?
Right.
Okay, so those would have to be 100 ohms each, right? Because 50 and 50 in parallel gives you, or sorry, 100 and 100 in parallel gives you 50. Well, but then those are in parallel. So really, actually, you need 100 and 100 here, which means you need 200 and 200 here, and 200 and 200 here. And how do you get that out of 50? And what you use is you use cables of known impedance, of known lengths that will perform the impedance transformation for you. And
that you're looking for.
If I remember,
and that's one way, right, Scott? Because then yeah.
I think it's ZIZL, but I don't remember how long the cable has to be. If it's a quarter,
So
that's a quarter wave. That's a quarter wave transformer, if I remember right. If it's a quarter wave transformer.
So the length of the cable it has more to do with the impedance of it than it does with the frequency you're going to be using it on.
Well, the frequency you're going to be using it on, that determines what the loss is going to be. And I actually had somebody here who was debating. They bought a 100-foot spool of cable and they only needed 40 feet on 70 centimeters. They were debating whether they wanted to cut their cable or not, or to just spool up the extra 60 feet.
Coil it up, right?
And I said, well, if on 70 centimeters, by leaving it there, you have another 4 dB of loss. Cut the cable.
This depends on the cable, right?
Yeah, cut the cable. You can always put it back together using connectors.
Or use a really high grade cable that doesn't tail off at 400. And it holds a lot of choices.
Yeah. And the cool thing is there are some really wrong answers, but there are a lot of not so wrong answers. And that's, a lot of experimentation.
Yeah, especially if it's like it's a fixed station. I've got to talk between here and that line of sight repeater up there. Do I need a lot of power to do that? A lot of energy? No.
I can't believe I remembered it. Look at that.
Oh, there you go. Good job.
Quarter wave transmission line. The formula is ZN over ZO is ZO over ZL, or Z naught, which is the transmission line segment that you're putting in, is Z naught squared is ZN/ZL. That's your transformer.
Scott, we just did a bunch of this stuff on an N7JI multi-band. It's got two balance and stubs and all of this stuff. And that dang antenna has come out resonant on all of the all the HF bands except for one. And it's legit. No losses. It's part of this went into that. It's really cool.
So also notice what they started with here. You notice what that is, everyone?
There it is.
There's your Smith chart.
Yep.
Yep.
That's cool.
And the
So
Smith
can
chart.
we say that? Yeah. Sorry.
Go ahead.
Can we say that the answer is that the length of the feed line definitely matters?
Oh, it doesn't always matter.
Most of the time, no. It's simple. Most of the time, it doesn't. But when you're doing what he's talking about here, this is a complex system.
Yeah.
Conversely, a single antenna, the feed line.
Probably not.
No.
Right.
But it can. There's always a qualified answer. So
trial and error. Cut it to fit.
Experiment.
Yeah, try it out.
Cut it to fit, and if it didn't work, you can always connect it back up.
Yeah, when you transmit, you have sparks flying off the front of your radio, like like I did when I was running my G5 RV that I built when I first got into ham radio.
I keep at 160 meters. I keep getting shocks from my tuner.
Yeah, right.
When I grab the knob.
What's going on with that?
Static, coming down from the antenna from picking up airwaves and grounding the case, or what?
I honestly, the problem is with 160 meters, you develop some very high voltages because your antennas, unless you have a lot of space, your antenna is electrically really short. So you can develop some really high voltages on the equipment in the equipment. And it's high enough that even though I've got a plastic knob, there's a little metal set screw in the knob. And if I happen to hit the set screw, okay, so here's a tree, right? And we're going to make a dipole. We're going to make a sloper, half-wave sloper, which is mounted in the tree. And then we use some rope that goes down to the ground. Okay, so if I feed this like this, ideally, this antenna being a dipole is 72 ohms. All right, so I could feed this with 75 ohm coax or 50 ohm coax and be reasonably close, right? But what if I build it and it doesn't work? I take a measurement down here and I get 126 ohms. And it's actually like 70 plus J 94 ohms. So that means it's resistive and inductive, right? Okay, what do I do with that? Why is it no longer 72 ohms?
Because the tree is
it's coupling with the damn tree.
Right.
This is like when you work with a real world, if you take a dipole and you put it in an anechoic chamber, an RF test chamber, and here's your dipole, this will be 72 ohms because all the walls of the chamber are non-reflective, right? That thing is in free space. It's 72 ohms. I can almost guarantee that's what it'll be. But as soon as you start doing something like, okay, you put a house over here, right? It couples with the house. You put a car on the street. It couples with the car. I mean, it'll be close, but okay, here's that tree. It couples with the tree. In the real world,
it'll interact with other antennas you've got up.
Yeah, it interacts with, it interacts with everything. So
EasyNet is handy.
You can model. You can try to model it using modeling software. That does sometimes work if you don't have too many things. But at some point, you just say, to hell with it. I'm just going to get as close as I can and use a tuner and then go. Because, like because I want to operate. I mean, I could spend all my time just perfecting it.
But resonance is a beautiful thing, Scott.
It is. It is. Because
That's why we like steppers.
Yeah, but they're such a pain in the ass to maintain.
Ours hasn't been. They
No,
freaking rock.
I know
Oh,
so many
love 'em.
people who've taken their step IRs and pulled them down.
Really?
Yeah.
God, we've been running ours for we got a vertical and a Yagi. Man, I'll tell you, that's
No, they're great antennas.
system. Wow.
They're great antennas, so long as the trombone doesn't,
Well, we don't have the trombone. I don't like the trombone.
Oh,
that's a lot of mass up there. They're kind of wonky in the air. They'll load up way worse with frost and snow.
Mm-hmm.
And so the straight element, yeah.
It breaks through the ice okay too?
We don't seem to have any problems. Yeah. It works really well. I love them.
Well, one thing you all have probably noticed is that we can talk about this stuff like all day.
Wait, there's the other thing, Scott. The other thing is, like I hear these guys, a guy says, what do you recommend? Okay.
Oh, yeah,
okay. So if you ask that question, then there are 10 hams on the call. You will get 10 different answers, maybe 11 or 12.
You get 100 different answers.
Yeah, exactly.
Yeah.
And what I would say is I can't answer that question until you give me more information.
Yeah. Well, it depends.
It depends. It depends on a lot of things.
We don't know. We don't know where our little, space is going to be here to use it until you get out there and start using it, I guess.
Yeah, exactly.
Everybody has a different part of it that, they're going to gravitate towards, I guess.
And it's going to change over time.
Mm-hmm.
Scott, your interest in amateur radio have changed. I mean, they've gone all over the place over 40 years, right?
Mm-hmm.
Mine too. They're always changing.
That is a sine wave.
Thank you.
Yes.
All right.
And as a new piece of equipment comes out, that changes again.
It does.
Gotta have
it.
Gotta have it.
I'm going to tell you, my world, when I saw what a waterfall looked like, my entire world changed. My whole operating world. Because
I love how that works.
I never had a waterfall display until I did. And so so you probably heard during the class, I'm a contester. I really like doing that. And one of the things about contesting is that I typically run low power unless I'm at somebody else's place. If I'm at somebody else's place and they've got a big antenna and high power, I will be happy to use it. But I don't want to maintain a big antenna. I don't want to have an amplifier. So I don't. I just, I have a relatively small station that works pretty well for a lot of things. And I'm able to pull off some things that I consider miracles sometimes. And I'm okay with that. I'm never going to be the biggest signal on the band, but I'm okay with that. But what that also means is that I have to be very cagey about operating sometimes and putting my signal where it's really going to work. And so let's say that I am looking at, I'm going to share this right here. So let's say there's a contest going on and I'm looking at the band. What I used to do is, because I did not have anything like a waterfall, I had to listen up and down the band and just listen for stuff, right? Okay, well, if I see something pop up, I would never just hear it. Let's say that this signal up at 28,465, right? And I was way down here. I would never know it was there. That might be a station that I really, really needed to contact for my score, that I could contact. And I was the first one to see it before everybody else saw it. And the pileup came crashing down on it because somebody put up a spot. I would never know it was there. But now I can look at this and say, okay, well, let's take a look down at the CW band. And okay, I can visualize this. I can actually see, okay, well, look, there's somebody down here at 025. And I can see what everything looks like. And I can then hear what I'm seeing. And so
yeah, after I seen that, I feel like I don't want a radio without it.
yeah, exactly. No, exactly.
I'm waiting
And
for a handheld. Do they make a handheld that
no,
has it?
no.
You don't
No,
need it
but
on
I mean,
VHF and
well, you don't
UHF
need it on
so
VHF,
much.
but if
no,
you're on HF,
Yeah.
But the thing is,
no,
so
but I definitely don't want one without it after seeing it because I feel like that's almost a necessity. It
yeah.
seems.
Well, it makes your world a lot. I mean, there are contests that I've been in where the band was so crowded that the waterfall didn't help.
Yeah.
And not only did the waterfall not help, it actually prevented me, if I just looked at it, prevented me from seeing the stations that were kind of like underneath the canopy of the trees, especially on CW, where I'd have the big ones, and squeezed in between the two really big ones was one small one, which was still audible, but you couldn't see it on the display.
You missed it because the display covered it.
Right, because it was the other signals were just so big that that little one just barely popped out, but I could hear it really well, and I could actually work them. And a lot of other people were ignoring that station because they weren't seeing it. So, you know, there's all kinds of cool stuff. But by
Sometimes
and
close
large,
your eyes and use your ears, man.
yeah, really. I mean, that's what I would do. I was doing, search and pounce during CQ Worldwide, and just, slowly tuning up the band, listening for new ones. It's what I grew up doing.
Run,
I'm
run,
glad
run,
you showed me
baby.
that on the internet.
Well, run, run,
I'm
run.
glad
If
you
you,
showed them ones on the internet because I like to just tune in and listen there and play around and get a feel for it.
Mhm.
And that's a nice place to go.
Oh yeah, the web SDRs are a wonderful thing.
Yeah.
But yeah, Kent, you know what? If I make it up to Alaska, or Steve lets me be one of his remote ops, that would be fun.
It's fun to operate up here. I mean, when it's good, it can be very difficult. High
Oh yeah.
latitude HF operation. All you guys, if you've never been, I've met so many guys, they think they know. I'm here to tell you, HF operation at high latitudes, above 60 degrees north, things change.
Mm-hmm.
It is way more difficult. The ionosphere, northern lights, all of this stuff.
It's affected
really,
much sooner.
yeah, it
I
just and
I
worse.
So I operated from I operated from OH5Z last year
Yeah,
during CQ Worldwide, and
man,
it was pretty wild. It was a lot of fun.
Something we've noticed lately, Scott. Have you seen this? There've been so many contests we work, and we hear Chinese stations calling CQ, and we got a
Yes.
big signal, and could never raise them, and they just keep calling CQ.
Mm-hmm.
And they're freaking deep because they got high noise floors or whatever's going on.
Yeah.
But I noticed, like in the last contest I did here, I don't know, it's been a number of months. All of a sudden, I worked every freaking Chinese station that was calling.
I have noticed that, and I don't know if
I don't know why.
I don't know why. Well, I know part of it is during the winter it seems to be a little easier for some reason. The summer it got really hard. But yeah, like a lot of stations that would call, like you can tell who's dealing with a lot of local noise. I mean, there was actually a guy I was trying to work on 160. Uh-oh, is Kent on the phone? Looks like he's on the phone. Uh-oh. All right, before I forget, I'm going to stop